All right, so I guess we'll get started. My name is Paulius Mitsikevičius. I'm one of the NVIDIA engineers, and today we'll talk about sort of Kepler architecture and optimization for it. So we've had these talks pretty much for all the GTCs that I've been at for the past several years, and the goals of this year's talk are a bit different from, let's say, GTC last year or GTC in 2010. Those talks tended to focus on diagnosing performance bottlenecks, diagnosing performance issues, and then suggest various optimization approaches to address them. This year, I'll focus more on how hardware operates and then relate hardware operation to various optimization advice. So it'll sort of be a complementary talk to what we've given in the previous years. So for really sort of full experience, in addition to this talk, I strongly suggest that you check out GTC presentations on optimization from 2012 and from 2010. As well as a number of talks this year on various profiling tools. So in the previous years, I would talk a lot about how to hack your code, how to look at raw profiler counters to figure out what performance issues are. By now, our performance profiling tools have improved dramatically. So a lot of that work you don't have to really do manually yourself. You can just rely on various profiling tools like Nsight, Visual Profiler, Command Line Profiler. And we've had a number of talks already, so a number of sessions these have already happened. But later on this afternoon at 3 p.m., there's a session on using Nsight, which is one of our profiling tools with integration into Visual Studio. But Nsight is also integrated into Eclipse if you work in Linux, which I'm guessing most of you do. Anyways, so outline for the talk today. So we'll start with examining how threads and warps execute on a single SM in a GPU. Then we'll sort of step a level above and see how threads and warps execute when you launch a kernel on a GPU and how different kernels interact and so forth. Then we'll move on to memory access, how hardware accesses memory, how to optimize to really extract the maximum performance out of the memory system. And we'll sort of close off looking at how much parallelism is needed to keep the GPU fully occupied. Now, this is slightly, the outline today is kind of opposite of the order of importance for various optimizations, right? So if we look at the order of importance, the most important thing is to provide enough work to GPU to keep it fully occupied, right? So level of parallelism is the most important optimization. After that, generally you'll want to optimize your memory accesses because most codes tend to be at least sensitive to memory bandwidth, if not limited by memory bandwidth. And lastly, you kind of worry about sort of vector execution, so you have to keep in mind that GPUs execute warps or these vectors of 32 threads at a time. So you want to look at your control flow and so forth. Now, so this is the order of importance for various optimization or analyses. But in order to explain why these are important and how things work, it's actually easier to start from the bottom up and go from hardware execution, warp execution, and build up from that. So that's the way we'll look at things today. Okay, so starting with thread and warp execution. You guys have probably already seen it several times that we mention over and over and over that GPUs are SIMT architectures. And SIMT stands for single instruction, multiple threads. And what that really means is that whenever we issue an instruction in hardware, it is executed by a warp of threads. And a warp is just NVIDIA's name for 32 consecutive threads. And we'll have some illustrations later on. Right, so a single instruction and multiple threads are executing that instruction at the same time. So it's not really the same thing as SIMD from the programmer's point of view because you don't have to program a vector yourself explicitly. Hardware will just take different threads and treat them as a vector underneath. So each thread is executing the same instruction, but it's providing its own arguments and values to that instruction. So once we look at a warp, then the question is how do warps relate to thread blocks, right? Because warps aren't really exposed to you as a programmer. They're there and they're easy to spot, but thread blocks are sort of the unit of work that you issue to GPU. So if you're familiar with CUDA, you know that thread blocks can be one-dimensional, two-dimensional, or three-dimensional. And that's purely convenience to the programmer. Hardware doesn't really care about the dimensionality of a thread block. From the hardware's point of view, it has a thread block. That thread block has some number n threads. That's all it really cares about. And now the hardware has to take that thread block and convert it into warps because it's going to execute, no matter what operation you issue, it's going to execute it one warp at a time. So if we have one-dimensional thread block, mapping to warps is kind of trivial, right? If we have 1D thread block, let me find my eraser, there it is. So the first warp will be the first group of consecutive 32 threads. So threads 0 through 31, that's your first warp. Threads 32 through 63, your second warp, and so on. Right? You just look at threads in consecutive order and say the first group of 32 is a warp and will be treated together as a vector of threads, and so on. If you have multidimensional thread blocks, so 2D, 3D thread blocks, what essentially happens, that multidimensional IDs are really logical IDs for threads. So you can sort of view mentally that you have to convert these to one-dimensional indices, like you would, let's say, in C, in row major order. And then when you have a one-dimensional list of threads, you go back to the same approach as for 1D thread blocks. First group of 32 threads, the first warp, and so on. Right? So that's essentially how things will get mapped to warps. Now, another thing that's important to realize is that whenever you launch a thread block, hardware will always allocate a discrete number of warps for that thread block. So if we look at an example where, let's say, we're launching a two-dimensional thread block, and its dimensions from the application's point of view are 40 by 2. So you have 40 threads per row and 2 rows of threads. So 80 threads from application's point of view in this thread block. Well, warp size is 32. So hardware will allocate the smallest number of warps that has at least that many threads. Right? So what's going to happen, really at the hardware level, you will get 96 threads worth of resources, right? Because you need at least 3 warps to contain 80 threads. And again, if we look at it, so sort of what I have in blue here, the first 32 threads, that's your first warp. In orange, that's going to be your second warp. We just continue on. And then the very last warp, actually, we don't fully utilize. So we use 16 threads to get to the 80 threads that application needs. And then, since we have to allocate discrete warps, we have 16 threads that are not really used by our application as well. So they will be masked out. You will get correct execution. But that's sort of something to keep in mind is that registers are still being consumed by those threads, and they're not doing any useful work to you. Also, when it comes time for this warp to execute instructions, as we'll see later on, it'll only be utilizing GPU or its resources at half efficiency. So actually, any questions so far? No. Great. Yes. I'm sorry, what was the question? Okay, so the question is, what are the idling threads doing? So maybe let me get back to that question in just a couple of slides when I'll talk about how we handle divergent control flow. Or in the next slide, I guess. Okay, so now that we've talked about warp, so if I'm issuing an instruction, the entire warp issues that same instruction. So the question is, what happens when you have to execute different control flow or different code on your machine, right? So if we look at 2 different warps, those 2 warps can execute entirely different code. There's no penalty on performance whatsoever, or no impact on performance. Because each warp keeps track of its own set of instructions. It does its own control flow, right? So one warp executing one code path, another warp executing another code path. Whether they belong to the same thread block or different thread blocks, it doesn't matter. They execute completely autonomously. There's no impact on performance. Now, to follow up on your question in the previous slide, what happens when only a portion of a threads in a warp have to execute that instruction, right? Whether they were masked out by hardware because hardware had to launch a discrete number of warps, so some threads were not really being used, or if you have an if statement in your code that says, if this is true, execute, otherwise don't execute that portion of the code, and some threads don't pass the test. Well, the mental model that I usually use for myself, just imagine that there's a bit mask for each warp, and if the value of the bit is 1, that means that warp has to execute a particular instruction. If the value is 0, that warp will actually not execute the instruction. It still spends time in that instruction, but it will not read its arguments. So if it's a memory access instruction, it will not go to memory and request that data. If every instruction produces a result, but if a thread is masked out, it will not modify the output, right? So output usually goes to either memory or register. It will not modify this output if that thread is masked out. So essentially, correctness is guaranteed because it's not really reading the inputs, it's not really writing the outputs, but that thread is still spending that time in that same instruction, so it's not executing any other code. So you're potentially wasting some computational resources when you mask out large numbers of threads. So we can also look at it sort of visually, right? So let's say we have a piece of code. So, this sort of C-like code. Let's say we have an if statement, and if the condition is true, we execute the code in the red portion, so that's the then clause. If the condition is false, then we execute the else clause, and we'll sort of indicated with green, let's say, instructions. Right? So in blue, I have code that all threads have to execute. It's not based on any condition. In red, we execute code that some threads have to execute based on the condition being true. And in green, it's a code path that's triggered by the condition being false. Right? And now let's say we look at two different warps. And in this particular example, the two warps execute different code paths based on that if statement. So for a while, they execute the blue instructions. They get to the conditional statement. They evaluate the conditional statement. And let's say the first warp here evaluated the condition to true. So it went to the sort of the red set of instructions or red portion of the code. Whereas the other warp evaluated the condition to false and went into the green portion of the code. So now they're executing different code paths, but again, those warps are independent. They don't really interfere with each other, so there's no performance impact. If we look at the case where you have different code paths within the warp, now there's impact on performance. And how significant that impact will be will depend really on your code and how much time you spend in these divergent code segments. But we can see here, now this particular warp gets to the conditional statement, and some threads have to execute the green path, some threads have to execute the red path. Well, the hardware is going to pick one path at a time, because again, all threads in a warp must execute the same instruction. It masks out all the threads that should not be executing that code path, and then later it'll fill up the masks and execute the code, the threads that have to execute the else clause. So here, let's say we have 3 threads that have to execute it, but the remaining, I guess, 29 threads out of 32 are still spending the time while these guys are doing useful work. Threads that don't have to execute the red path, they can't really jump ahead and start executing code that's useful. They have to all be in lockstep within the warp. And later we flip the mask and we do the opposite. Now the other threads are executing the code, and the codes in the threads that executed the red code are just sort of hanging around waiting for them to finish. So I guess hopefully that answers your question. How significant that is, like as I mentioned, it really will depend on your code, right? If you have some if statements, but you spend 5% of your execution time in a divergent code, it really doesn't matter, right? So that particular portion of the code might take longer now, twice as long or however, but it's a small portion of the code. On the flip side, if 80% of the execution time is spent in code that diverges, has to go into different control paths per warp, you are probably leaving a lot of hardware pipelines idling, waiting on threads that have to execute the code. Okay, so that's control flow. Another thing that's interesting is to understand how GPUs really execute instructions, because they are slightly different from CPUs. They actually are a lot simpler than CPUs, even though CPUs are sort of also beginning to move back in this direction. So all the instructions are executed in order. Right? So compiler takes your source code, it generates a sequence of instructions at the machine language level. And the hardware will go through that set of instructions that the compiler arranged in that order. GPUs don't do any speculative execution. We don't really do branch prediction, so we just execute the instruction in sequence. Whenever hardware gets to an instruction where, let's say, we don't know which way the branch is going to go, or some instruction arguments aren't ready, that instruction will stall until all the requirements have been fulfilled. So as long as instruction is eligible, it can get issued. And if we look at a particular instruction, it's not eligible, or I guess the other way. An instruction is eligible if both of the following conditions are true. Right? So these are 2 bullets here. One of these days I'll figure out how to look at the laser pointer. Okay, so any instruction to execute needs 2 things. It needs the arguments, right? So let's say if it's an integer add instruction, it needs to have the values that it has to add. Those values have to be ready, and they might be produced by a previous instruction. So we have to make sure that if a given instruction's arguments are produced by somebody else, that somebody else has completed the operation and the values are ready. Right? So that's essentially instruction dependencies. Also, you need the pipeline for the particular execution to be ready. And as we'll see in a moment, GPUs have different pipelines for floating point instructions. Double precision floating point instructions go into different pipelines, memory access pipelines. So there are a number of different pipelines within an SM on a GPU. And some of those pipelines might be busy when instruction comes about. So again, even if the arguments are ready, but the pipeline is still occupied, that instruction will have to stall and wait for the pipeline to free up. Okay, so latency hiding. I guess we sort of alluded to that. So latency really is incurred whenever an instruction, let's say a pipeline is ready, but arguments for that instruction are not ready because they are still being produced by some other previous instruction. So GPUs are pipelined architectures. So as I mentioned here, the latency for a given instruction, and the latency here is from the moment the instruction starts to execute until its output is ready to be consumed by some other instruction. It varies by instruction type, but it's roughly in the neighborhood between 10 and 20 clock cycles. Right? So if we do some operation, the value is not really produced until 20 cycles later. So if you have a situation where you have one instruction, let's say, producing a value, and the immediately succeeding instruction consuming that value, you'll have to wait between 10 and 20 cycles before you can execute the second instruction. So at this point, the warp will stall, and again, you're wasting hardware resources. So there are two ways to hide that latency. One way is with instruction-level parallelism, right? So that's where the pointer over here. So that's where even within a single code stream, you have independent instructions between two dependent ones. And that's, I guess, easier to show. So if we look at this quick example, I just grabbed one of the kernels I looked at and looked at the assembly of it. So FFMA is a floating point multiply add instruction. The first argument is always the destination. So we actually will multiply registers 43 and 0, add 4 to that, and store the result into register 0. And if we look through the instruction stream, register 0, which is really the output of this particular instruction, is now consumed by this floating point multiply instruction later on, right? So R0, so that's the dependency sort of outlined in red. And here we'll have to wait essentially around 10 clock cycles before this R0 is ready for the multiply instruction to consume. In between, we have another floating point multiply instruction, and it is not dependent on register 0. It's not consuming register 0. So we can assume we issue this instruction in one clock tick. After that, we can issue the following instruction because they are independent. So for this code, we'd say we have an ILP or instruction level parallelism of 2, because if we look at any pair of sort of adjacent instructions, any pair of adjacent instructions, they're not dependent on each other. Right? So we can issue one instruction, issue the next one, and then we stall waiting for the very first instruction to produce its value. So that's one way to hide parallel latencies, and that's really mostly what CPUs rely on. Was there a question in the back, or? Okay, so I'll repeat your question. Correct me if I misunderstood it. So the question was, if you have some complex math operations in your code, how good is the compiler in arranging them at the assembly level to expose as much ILP as possible? Is that correct? Okay. So compiler actually is pretty good. It's pretty popular for people to complain about the compiler, and I've complained plenty about it as well. So compiler has a pretty tough task. It has several competing goals to achieve. So it needs to expose more ILP. At the same time, it often needs to conserve registers, and those are semi-conflicting things. So it's a tough task for the compiler to do, but I would say in most cases, compiler does a really good job. There are some cases where it trips up. Right? And I'll show you in a little bit how to actually look at assembly code. So if you suspect that compiler is not doing the right thing, nowadays you have at least a way to verify whether your hypothesis is true or not. If you have your source code, if you're willing, you can actually look at machine assembly and see is the compiler doing a good job or is it doing a poor job. And if you determine it is doing a poor job, you should just file a bug. So there's a way for you guys to file bugs with NVIDIA, and then compiler team will look at it and hopefully address it. But in general, I'd say it does a pretty good job. Yeah. Okay, the question was, is there a concept of a branch hint? No, there is not. So we basically wait for the branch target to be resolved, then we execute the instruction that we should. Yes? Okay. Yeah, so your question actually, I won't repeat it, but I'll just switch, I guess, to the last major bullet here. So ILP is one way to hide instruction latency, right? If you have two dependent instructions, you hope that compiler squeezes in independent instructions in between, and you can continue to execute while waiting for the result that you need to be produced. Another way, and that's really what GPUs rely on a lot, is to just switch to another warp. Right? So, and this will take us sort of in the direction why GPUs use so many warps running at the same time, or so many threads. It's really for latency hiding. So if one warp stalls, it cannot execute its instruction, At this point, hardware would idle. But if you have enough warps waiting around, and at least one of those other warps is ready to execute its instruction, hardware will switch to that warp on the SM and start executing its instruction. And unlike on CPUs, switching between these warps or threads on a GPU is free. Unlike the CPUs or GPUs do the switch for free because the state for any thread or warp is partitioned. It's not stored, restored on these switches. And in general, right, if you have one warp stalls for n cycles and you have no instruction level parallelism, if you have n other warps on that particular SM, and really that instruction scheduler, as we'll see in a moment, is just as good. So really hardware doesn't care whether independent instructions are coming from the same thread or from different warps. Right? By definition, instructions in different warps will be independent unless you have synchronization primitives there. Okay, so looking more now at Kepler instruction issue. So this was how an instruction stream for a given warp is executed in hardware. Now, if we look at a Kepler SM, it's actually more complex and more powerful. So each Kepler SM has 4 instruction schedulers, right? And depending on a chip that you're looking at, there are between 1 and 14 SMs today. Right? So the high-end K20X board has 14 SMs, and so on. But each of those SMs has its own instruction schedulers, and it has 4 of them. And what happens, all the warps that are running on a given multiprocessor, they get partitioned across these 4 instruction schedulers. So once a warp is assigned to instruction scheduler, it stays there, and that instruction scheduler is responsible for that particular warp. And that scheduler tracks of all the warps that it has. It tracks which of its warps are ready to execute the instruction, which warps are stalled, and it essentially picks out of the pool of the warps that are eligible to issue an instruction and executes one of them. On top of that, for any given warp, a scheduler can dual issue instructions. So from a given warp, a scheduler can take 2 adjacent instructions, and if they are independent of each other, and pipelines for execution of both of those instructions are ready and available, then we'll actually issue 2 instructions in the same clock tick from a given warp. So that's why if you look at the peak instruction issue rate for a scheduler is 2, they come from the same warp. The peak instruction issue rate for an SM is 8, because you have 4 schedulers, they work on their own, unless you have to synchronize the warps, and then each of those 4 schedulers could potentially issue 2 instructions. So you can actually hit that peak, you just cannot sustain it because we start running out of pipelines and instruction cache lanes and so forth. So what's sustainable if you sat down and wrote pretty synthetic code, and your goal was to only achieve the maximum instruction throughput, so you chose a fortuitous sequence of instructions, you could actually sustain about 7 warps worth of instructions being issued every clock tick in a single SM. As a rule of thumb, if you have code that should be arithmetic or instruction limited as opposed to memory limited, if you're getting about 4 or 5 warps worth of instructions issued every clock tick per SM, you're doing pretty well. And that's something that, for example, again, the profiling tools will tell you. They will report this instructions per clock cycle, and really look at instructions per warp. So really say, well, 4 or 5 warps worth of instructions. So it would report IPC of 4 or 5 or so forth. If I get to that stage, I generally don't really try and get higher IPC. And by definition, code that's memory limited or code that's latency limited, and we'll look at latency a little bit later on, that code will achieve low IPC because the limitation lies elsewhere. It doesn't lie within the SM. Yeah. Yes. So the question was, does the profiler give you the number of achieved instructions per clock cycle? Yes. So it gives you the IPC. Is that question?
So if you have, say, 128 threads in a block, 4 warps,
okay.
Are those 4 warps guaranteed to be on separate instruction schedulers?
Okay, so a very good question. The question was, let's say you launch a thread block, and you have 128 threads in a thread block, so that's 4 warps. And how do those warps get assigned to schedulers? That's correct. So the warps will get assigned to different schedulers in round-robin order. So if you have a thread block with at least 2 warps, they're guaranteed to be in different schedulers. Okay, so the question was, what are these numbers like for Fermi? Let me see if I can remember those off the top of my head. So Fermi has 2, it depends on the Fermi chip. So the high-end compute chips, they have 2 schedulers, and they do not do dual issue. But Fermi, on the flip side, has more SMs. It has up to 30 SMs. There's another question here. Okay, another good question. So the question was, can a scheduler steal warps from another scheduler? So let's say if scheduler 0 doesn't have any warps eligible to execute, but scheduler 1 has plenty of warps with instructions ready, can the warps migrate? The answer is no. Once a warp is assigned to a scheduler, that's it. It stays there. It doesn't migrate. Okay. So in order to keep an SM busy, we'll for a moment pretend that we have code that's instruction limited. So because of these 4 schedulers and warps getting partitioned across the schedulers and no warp stealing happening, we need at least 4 warps to occupy the SM. In practice, I would say even if you have infinite ILP, you would really need 8 warps because we can't really issue 2 instructions back to back from the same warp. We have to have at least 1 instruction from another warp in the next clock cycle. But either 4, I keep pressing the wrong button. There we go. So either 4 or 8 warps per SM is still a very, very small number. You would have to have a very large instruction level parallelism to hide the instruction latencies. And some codes actually are capable of doing that. So if you look at GTC 2010 presentation by Vasily Volkov, he talked about achieving good performance with very, very low counts of warps per SM. But you have to be very careful when you're doing that because you run the risk of starving the SM. Now, so essentially, an SM can actually track up to 64 warps. That's how many warp IDs each SM has, so you could have plenty of warps running on it. You may not be able to reach that high count of warps concurrently on an SM based on your register consumption or shared memory consumption, but that's the most an SM in Kepler can track. And those warps can come from different thread blocks. On Kepler and Fermi, they can even come from different kernels, right? Because now an SM can concurrently execute different kernels. And the hardware really doesn't care where a warp comes from. If it's executing the same thread block, different kernel, grid altogether, it just needs a warp with an instruction ready to execute. So if we look at instruction-limited codes and assume that we have no instruction-level parallelism, or let's say instruction-level parallelism of 2, you'll need 40 or more warps per SM running concurrently or running at the same time. Right? Again, you have 4 schedulers. Instruction latency, basically the minimum is around 10. So to hide that latency, you'll have to have 10 warps per scheduler times 4 schedulers, 40 warps. You may get away with fewer if you have instruction-level parallelism. If you have longer latency instructions, like the 20, 24 cycle latency instructions, you may need more warps. So as a rule of thumb, what I usually think of when I start coding and trying to shoot or aim for some occupancy per SM, I try to have about 32 warps per Kepler SM, and then I profile the code, see what the profiler says, and try to adjust. If I need more warps, I see can I increase the occupancy beyond that. So as a starting point, if you need a hint, sort of aim for 32 warps per SM, so that's 1,024 threads, and go from there when you write your code. So you'll notice that up until now, I never mentioned CUDA cores, right? So CUDA core is a bit of a controversial name because it's a GPU core, so it's not only NVIDIA, right? So GPUs from both AMD and NVIDIA, the terminology actually predates compute-capable GPUs. Traditionally, they count as cores single precision floating point pipelines, right? Which is different from CPU's definition of a core. And if you look at, let's say, network hardware, network switches, they have their own sub-definition of a core. So core is a highly overloaded term. But oftentimes I see people make a mistake. Let's say if they look at a Kepler SM, they say, well, it has 192 CUDA cores, and the entire chip has 2,600 CUDA cores. And then I sort of go with my experience on the CPU and say, I need 2,600 threads to keep this GPU busy. And if you do that, in the vast majority of the cases, you will not be exposing enough parallelism to GPU. You'll be stalling and waiting on latencies. Right? So keep in mind that GPU core, not just NVIDIA GPUs, are single precision floating point pipelines. What you really need is you need enough threads to hide latencies that your code incurs. And if your code is really purely single precision code, then you worry about CUDA core count. But many codes actually have higher latencies than single precision, so you'll generally need more threads than there are CUDA cores in that chip. So, as a quick note, Don't try to tie the number of threads for performance with the number of CUDA cores. Sort of look at the latencies you have to hide, and really look at the profiling data, and Profiler will actually tell you that you're leaving GPU idle, which generally means you need to give it more work. So any questions on CUDA cores before we move on? Yes? Yep. Okay, so the question was, as a rule of thumb, I suggested that you start with 32 warps, and can they come in any number of thread blocks? Theoretically, yes. NSM also has limitation, and we'll see that towards the end. So NSM can run up to 64 warps. That's the IDs that the hardware has. It also has a limit on the number of thread blocks that it can track at any given point. And I forget that number off the top of my head, but it's somewhere in subsequent slides that are coming up later. I think it's 16 or something like that. So if you have single warp thread blocks, you may not be able to get to the required parallelism. But we'll have some slides on that later on. Okay, so now that I'm done with CUDA cores, let's look at the diagram of NSM. So this is a diagram taken out of the Kepler white paper, which came out last year. And it's very busy. It has a lot of things, but the concepts are really pretty simple. So these green things are the CUDA cores, the single precision floating point pipelines, and there are 192 really single precision lanes per SM. That means that any clock tick we can really issue 192 threads worth of a single precision floating point operations because we have all of these lanes. And these lanes are per thread, right? So they'll be somehow divided among the warps. So this is I guess, GK110 chip. So I guess in yellow here, we have double precision units, so that's 64-bit floating point pipelines. So this now suggests that 64 double precision throughput-wise, throughput is 1/3 of what's available in single precision. Then we have SFU, or special function unit pipelines, of which there are 32. So these are, I guess, slightly different greens over here, and these guys over here. So there's a total of 32 of those, which means that in any given clock tick, you can issue 32 threads worth of instructions to those pipes. And they do things like integer, multiplies, transcendentals, sine, cosine, and so forth. Whereas the single precision cores, they actually are capable of other instructions as well. They can execute integer, simple integer operations like add, min, max, and so forth. And for more details, if you look at the CUDA programming guide, it actually tells you which instructions map to pipelines of what throughput and width. We also have, essentially lanes for executing memory load store instructions for both shared memory, global memory, and we also have texture lanes. So these are at the bottom here, and there are 16 of those. And we'll take a look at how memory is accessed a little bit later on today. I think here I mostly repeat the same information. So if we look at the single precision cores, there are 192 of them. So it's really 6 warps worth of instructions. And the reason I put 6 warps worth in quotes is because if you remember, if we go back, we have 4 schedulers. Each scheduler can issue 1 warp in a clock tick. So this already tells us that to really utilize the potential of single precision throughput on a GPU, you must have ILP in order to issue 2 instructions at a time per warp, right? Because if we can only issue 1 instruction per warp at a time, we have 4 schedulers, 32 threads in a warp, so we can really only issue 128 threads worth of instructions per clock tick if you're not exposing ILP for dual issue. Right, so really to get to this 192 threads worth of instructions per clock tick, you have to have instruction level parallelism in your code. And many codes have it. And that's where, I guess, taking a look at assembly helps. Memory access, we'll look at it in detail. Double precision, one interesting thing to note here is that double precision instructions on Kepler will require 2 cycles to issue. We saw we have 64 pipes, so 2 warps worth of, but there are 4 schedulers. And the mental model here, if you like, you could sort of think that you have 64 lanes, and those 64 lanes are divided among those 4 schedulers. So each scheduler gets 16 lanes, therefore to issue a warp, it'll need 2 clock ticks. Right? So when you profile your code, you might see there's replays in your code, and if you have double precision instructions, some of those replays are coming just from double precision instructions needing 2 cycles to issue. And for more details, go to CUDA programming guide. There's actually a table. If you look at the programming guide online, not in a PDF, there aren't section IDs that can give you, so just search for it for a table named throughput of native arithmetic instructions, and actually for all the arithmetic operations, it tells you what the throughput is, which you can immediately then relate it to one of these pipes based on their width. Okay, so examining assembly, I mentioned that earlier, but now if you're really trying to tune your code very close to the metal, to get the last few % of performance, sometimes it might be interesting to look at assembly. Right? So keep in mind that there are two levels of assembly in GPUs. There's PTX, which is a virtual assembly, and there's machine language that we call SAS. So PTX is virtual assembly. It's actually forward compatible with future GPUs. And it can also be inlined into your CUDA C code. And I think CUDA Fortran compilers either already allow it or will allow it soon. Right? So if you want to do some assembly inlining, it would be done at PTX level. But you do have to notice that it's not the final code that executes on the hardware, and it's not finally optimized code if you are looking at PTX disassembly. What hardware executes is really machine language instructions. Right? Those are architecture specific, and those we do change from generation to generation of GPUs. So at assembly level, at machine language level, we don't have backward or forward compatibility, which is the reason for PTX. And whenever you compile your code, if you compile without any specific options, it actually will compile to specific architecture, so it'll generate machine language. But in addition to that, we will store in the executable the virtual assembly PTX, so that if you run the same executable on a different piece of hardware for which you compiled, the driver at that point, it does contain a compiler. It'll start with a virtual assembly and JIT it to machine assembly of that particular GPU. Anyway, so generally for optimization, if I look at assembly, I want to look at the final assembly that hardware will be executing. So you look at the machine language. So with every CUDA toolkit, you get the cuOpsDump utility. Right? So it's opsdump is the traditional Linux utility to look at assembly of CPU executables. So add Q to that, and you can look at GPU executables. To look at PTX or virtual assembly, you essentially run the utility, give it a -PTX option, and then you give it an object file or executable name, and actually will dump out all the assembly for it. There are additional options to look at specific functions and so forth. To look at final machine language assembly, instead of PTX, you specify -SAS, and this will give you machine assembly. And there are documents that come with every toolkit on PTX spec of the language, as well as the instruction set for each compute capability. Those names sometimes change, so if you just look at the docs directory of your CUDA toolkit install, you'll see those PDFs there. Okay, so the takeaways. So the main takeaway is that you have to have enough threads or warps to keep the SM busy and executing, right, to keep it from stalling. And don't think of the number of threads that you need in terms of CUDA cores. Sort of just think more generally in terms of latency hiding. If you know that your code is instruction throughput limited, so the profile, let's say, says that you're limited by arithmetic, not memory, then you have several avenues, right? So we saw that we have different pipelines for different instruction types. And some pipelines have more resources than others, right? Single precision has a lot more resources than double precision pipelines. So try, if you're instruction limited, try to use as many operations that would go to these wide pipelines, right? So let's say do double precision only when absolutely necessary. Do single precision as much as possible because you have a lot more single precision throughput. Another example would be use intrinsics. So let's say you have to compute sine or cosine in your code, or logarithm or square root. We do come with a standard math.h implementation, which gives you the same precision as you would get on CPU. But if you are willing to sacrifice a couple of bits of precision, right, so instead of getting 24-bit mantises, you get 22-bit mantises in a number of these intrinsics. There are intrinsic functions that come, they're preceded with __ sinf. So any sort of math.h function that has a counterpart preceded by __, it actually executes as a single assembly instruction in that special function pipeline. And instead of being a sequence, a software sequence of instructions, so let's say compute the sine, you get the answer in a single instruction. Slower precision, but much, much faster. So again, something to consider. If you can sacrifice some precision, there's potentially performance to be gained. And again, more details on all of these intrinsics are in the CUDA programming guide. And finally, if you're instruction limited, at that point you also have to consider sort of the warp divergence, or whether you have these cases where you execute significant portion of time different code paths within individual warps. So a question there. Okay, so the question was, won't the CUDA compiler translate multiplications to intrinsics? No. So by default, CUDA compiler assumes that you want the same precision as you would get, let's say, with standard math.h operations. So it will not use intrinsics unless you specifically request them. And you can actually use other intrinsics explicitly in your code yourself. And compiler does have an option, I think, called -fastmath, where it'll go and replace all the operations that it can with intrinsics. But by default, unless you specifically request it, either through intrinsic use or compiler flags, it will go for maximum precision. I think there was another question, yeah. Okay. So the question was that some documentation claims that compiler provides latency information to the hardware. Yes, so for some assembly instructions, compiler knows the latency of a given operation, so it might provide a hint to the compiler that, if compiler detects a dependency chain, it might provide that information to hardware ahead of time, so hardware can just quicker figure out, well, what's the dependency chain, and will I be able to execute the next instruction, or will I have to wait, X number of cycles? So the question is, when you disassemble, will you see those numbers? That I'm not sure about. I'm not sure. Okay, so this was all sort of focused on a single SM and how we execute, a given warp or given set of warps running on a single SM and optimizations for that. If we look at a larger picture, so kernel execution, when we launch a kernel, we launch some number of thread blocks. So here, we have kernel launch syntax. We launch 1,024 thread blocks. Right? So now how do those get spread out across the SMs? And actually, that is pretty simple. So we look at a set of thread blocks and start assigning them to different SMs. And a thread block is assigned to an SM if that SM has resources available. And resources mean registers, shared memory, and things like warp slots, thread block slots, and so forth. Right? So if SM can execute a thread block, it will take the next one if it's available. One thing is that, okay, so that's a good point to look at. So thread blocks that haven't been assigned wait for resources to free up. And we really assign thread blocks at thread block granularity. So let's say SM ran and has enough resources. Let's say we have 128 thread blocks, so 4 warps in a single thread block. But SM only has enough resources for 2 warps at this particular moment. We will not go and schedule the first 2 warps of a thread block and then wait for more resources to free up to schedule the remainder of a thread block. So we always wait for enough resources for the entire thread block before it gets assigned to an SM. And then a given thread block does not release its resources until all of its threads complete execution. So let's say if you launch 128 threads, and 127 of them immediately say, check some conditional and exit. They call return. But one thread out of 128 continues to execute. As far as hardware is concerned, all 128 threads are still consuming resources and preventing other thread blocks from getting scheduled. So that's how we partition thread blocks. And I guess the last bullet we kind of answered in a question earlier. So once a thread block is assigned to an SM, we look at all the warps from that thread block, and they just get assigned to different schedulers in round-robin order. Okay, so concurrent kernel execution. So that's how things happen whenever you launch a single kernel and it runs by itself. Now, Fermi and Kepler are both capable of executing several kernels at the same time. The general stream rules do apply in this case, like with any other calls. So for 2 kernels to execute, they have to be issued to different streams, and there must not be any synchronization calls between those kernel launches. But if you have such a case, the way kernel processing is going to happen is that first we will look at the current grid or current kernel and start assigning its thread blocks to the SMs. And the reason I put current, because current definition is kind of nebulous or fuzzy. So I'll get back to that in a moment. Now, once you have assigned, and once you look at the current kernel launch, and you have assigned all the thread blocks to some SMs may still have resources available. So if that's the case, then the hardware will actually look other kernels that are eligible to execute from some other streams. And if there are, it will try to go and start assigning the next grid launches or the next kernel launches thread blocks to the SMs that have resources and start sort of backfilling them. It'll keep doing that until it runs out of SM resources. And at that point, it waits for some thread block to finish, free up resources. So it's going to look at the next waiting thread block and assign that. So if we look at the definition sort of the next grid, It sort of varies by compute capability. So in compute capability 3.5, so these are your GeForce Titan and Kepler K20 GPUs or GK110 based GPUs. Really, the next grade is any kernel issued to a different stream, because with hyperqueue functionality, if you issue several calls to different stream, hardware, semantically, hardware is free to execute them in any order, including at the same time, as long as there are no synchronization points between them. Now, pre-compute capability 3.5, what hardware really did, it considered all the launches of the kernels in sequence that they appeared in your source code, right? Because it only had one queue instead of many queues for execution. So if you had kernel 1, kernel 2, it would inspect them in that order as they appeared in your source code. Now hardware actually has multiple queues that it looks at. Therefore, if you issued kernel 1, 2, and 3, and they go to different streams, you might execute kernel 3 first, and then start backfilling with kernel 2 and kernel 1, or execute kernel 1, then kernel 3, kernel 2, and so forth. Right? So compute capability 3.5 made things a lot more flexible, which is nice. And the only caveat to keep in mind is that if you do issue kernels to different streams, but you want them to execute them in a particular order, you'll have to put synchronization primitives now in there yourself to really enforce the order. There are limits on concurrent kernels running on a GPU. So compute capability 3.5 can do 32 at a time, and actually you can have 32 different kernels running on a given SM if we can track 32 thread blocks, which I think we can't, but anyway. Previous compute capabilities could run 16 different kernels per chip at the same time. So you may have heard that in CUDA 5.5 and compute capability 3.5 GPUs, we will have priorities. So there are two levels of priority. There's the default priority and high priority. So you have a high priority stream, and you can issue calls to that stream. So this changes a little bit how thread blocks are assigned to the SMs. So if you have kernel, let's say, running some thread blocks running in a default stream on the SMs already, and now you launch some work that goes into a high priority stream. So kernel launched into a high priority stream. What's going to happen is that we will not preempt already executing thread blocks, so those will be allowed to run to completion. But as default priority thread blocks start completing, high priority thread blocks will jump to the head of the queue. Right? So they will get past all the other default priority thread blocks waiting to get assigned, and they will get assigned first. The high priority thread blocks will get assigned first to the SMs, and therefore, as the name suggests, they execute at a higher priority. Right, so it's really pretty simple when you think about it. Whatever's already been assigned to the SM will finish executing. Things that haven't been assigned, if they're default priority, they wait, and high priority work goes first. And again, all the concurrent kernel requirements apply. So stream rules apply if you issue, let's say, a default priority kernel to stream X, and then a high priority kernel to the same stream X. If you issue two different calls to the same stream, you're telling the hardware that these two calls are dependent and should be executed in that order. So even though the second call has higher priority, it will wait for the first call to finish because we have to guarantee correctness. Even if it's higher priority work, it can't really jump ahead and execute ahead of things that produce the results for it. Correct. So the question was, is priority per launch or per stream? So priority is per stream, yes. Correct. So I forget the exact API, but I think when you call CUDA stream create, I think there's CUDA stream create with flags, and there's additional arguments you pass to the stream creation saying that it's a high priority stream. And afterwards, you just use it like you would any other stream. Okay, so CDP, which is CUDA dynamic parallelism. So starting with compute capability 3.5, a GPU thread running on GPU can actually launch a grid or launch a kernel to run on GPU as well. And for the most part, it's handled just like any other kernel launch from the CPU side, with one exception. Because you do have cases where a GPU thread will launch a kernel, and then later in your code you might call CUDA stream synchronize or CUDA device synchronize. And again, these synchronizations are being called by a GPU thread, not CPU thread. So essentially what this tells the hardware and the software system is that, well, I launched a set of threads to do some work, and by calling, let's say, CUDA device synchronize, I'm really saying I need for those threads to finish before I can make forward progress on my own. Right? So the parent that launched additional threads has to wait for the children to complete execution. So in this case, what's going to happen, we will take the thread block that issued the kernel launch and that called the synchronization primitive, and we'll swap it out from the GPU to free up thread block slots. And this guarantees that we can start executing the grid that was just launched, right? So we don't end up with a deadlock situation. And once the child threads have completed execution, we restore the context of the thread block that just performed that launch, and it will get its chance to finish execution. Right? So that's how things are being done today. In general, really, we always guarantee forward progress so that if some thread launches a set of other threads to execute on GPU and then syncs, waiting on them to finish, you will not incur deadlock. How we implement it underneath may change in the future. Right? So really the important takeaway is that forward progress will be guaranteed from now on. However, that probably does have performance implications, right? Because something may have to get swapped out from GPU and then restored later on. And at this point, you are doing context store restore. So things like registers and shared memory state of a particular thread block now have to be saved to DRAM and then brought back later, which does have some overhead. And I guess another sort of semantic thing is that a thread block completes only once all of its child grids have also completed execution. So even if you don't synchronize, let's say I have a thread block, one thread launched 1,000 other threads, and now really this particular thread block, all threads complete execution. Well, that thread block doesn't really get removed from the SM until all of its children have finished execution. Yeah, question? Okay. Yeah, so the question is it possible to perform recursive calls? And the answer is yes. So you can a kernel can recursively launch the same code again for a number of threads. But actually, that was possible even without CUDA dynamic parallelism. So even Fermi GPUs, you could recursively call functions. The only restriction on compute capabilities lower than 3.5 is that if you had recursion, a thread could only call a function for itself over and over and over recursively. Now you can actually launch multiple threads. So you can have a single thread running, it launched 1,000 threads. And then each of those 1,000 threads can launch again the same function for another number of threads and so forth. Okay, so the takeaways here is that when you launch a grid of thread blocks, they'll get partitioned across the SMs. Now, to keep an SM busy, we saw that you need a certain number of warps, certain number of thread blocks running on that SM simultaneously. So if you have a chip with many SMs, you need that many more warps and thread blocks launched to occupy the entire chip, not just a single SM. Concurrent kernels, generally they will help if your individual grids don't have enough work for GPU. So you might have a situation where just because of your functionality of your code, you launch some work for GPU, one kernel, it just doesn't give enough work to the GPU to occupy it. But if you have independent functions, you can actually launch them simultaneously. They will execute in different streams at the same time. And together, several concurrently running kernels could be actually fully utilizing the GPU. Streams, the upcoming feature. So those are useful if you have some long executing kernels and periodically you get some other piece of work that you really need to compute the result for as soon as possible without waiting all the previously issued work for all the previously issued work to finish. Right, so that's when you create high priority streams and you issue high priority work to those streams and you get your answers at a higher priority. And CUDA dynamic parallelism, so it adds flexibility to your coding approaches, right? So you have recursion, you can call kernels, but you have to be aware of that. If you have synchronization primitives when using CDP, that will generally imply store and restore of some thread block context, which will take some time. Yes? Okay, so the question was, I say, may cause store restore. So the question was, like, in what situations there would not be a context store restore cost? So let's say if you have, SM still have plenty of resources to run the children without swapping out the parent. I'm not positive about what the current implementation does, but conceptually that'd be perfectly fine, right? Okay, so the question is, how does that show up in the profiler? That I don't know. Yeah, I have no clue actually for that, so I'm not going to try and make up an answer. Yes, Jim? Okay, so the question is, how many thread blocks can an SM have active at any one time? I want to say 16. I have that number later on. So I think Kepler SIM can track either 16 or 32 blocks. We'll see it later on. Yeah.
What type of applications end up with small number of grids?
Okay, so the question was what type? Yeah, that's later on. So the question was what type of applications end up with small grids. I'm trying to think of something off the top of my head. I mean, it would really depend. Let's say you're doing some work. Let's say you have a two-dimensional grid. And just because of let's say the relationship between the grid cells, you kind of need the cells above and left to have produced a new value, right? So it's sort of you have a front advancing through your data. So at the very beginning, if you launch, so you have to process one cell at the beginning, then afterwards two, sort of this expanding diagonal, right? So very early on, there just may not be enough work for GPU just because of the way application is set up or the way the equations are set up, right? So that's where a single launch is not keeping the GPU busy. If you just happen to have some other functions that could be running at the same time that are independent of that, you don't have to now hack your code around and still launch a single kernel that really does two different things. You can have specific kernel executing one code and another kernel, source code that executes a different code and just launch them concurrently. But it actually happens not that frequently, but we do run into those cases. Okay, so memory access, where we'll spend, I think, most of the time. I think I spent on this portion longer than I thought. Okay, so memory optimization is probably the most important technique after exposing sufficient parallelism to GPU, because many algorithms, if not most of them, are memory limited. If we look at arithmetic intensity, it's not uncommon for various algorithms to have one operation per byte accessed in memory. Right? If we look at modern processors, not just GPUs, if you look at, let's say, x86 sockets, all of these processors have, if we look at its peak, like say flops or integer operations, and peak memory bandwidths, and we take a ratio of those. Those ratios are somewhere between 4 and 9 today, or I guess 4 and 10, as I say here. So hardware has a lot more throughput in arithmetic than memory bandwidth, right? So if you take some chip and you look at the gigaflops divided by gigabytes per second, right, you'll get this ratio that's 4 to 10. And then if you match it up to what's really happening in the code, that ratio is generally much smaller at the instruction level. So that's why many codes are at least sensitive to memory bandwidth. Therefore, it's important to extract maximum performance out of your memory system. And GPUs do have a lot of memory bandwidth, right? In excess of 200 gigabytes per second at the DRAM level. But you have to observe certain rules to really extract all of that bandwidth. So when optimizing memory access, there are two general ideas. So the first one is you want to maximize the use of bytes that travel across the bus. And we'll look at that in quite a bit of detail, right? Because when you access memory, you get some discrete chunk of bytes. So you pay for all of them to arrive. Therefore, you might as well, or you would prefer to use them all. The other one is to have sufficient concurrent memory accesses, because you have to have enough work for the memory bus to keep it saturated. And we'll have some examples of that. So if we look at a memory system in general on Kepler, right? So we have some number of SMs that do the actual arithmetic and execution. And at the bottom here, we have DRAM, right? So that's up to 6 gigabytes today. It has 250 gigabytes per second on the highest end GPUs. Two things to keep in mind. When we access DRAM, so all the data starts out in DRAM and has to make its way to the SMs in order to be processed. When we access DRAM, we don't access just the word that we need. Let's say if you need to fetch a single Boolean value, which might be a single byte, right? You will get at least 32 bytes out of DRAM. So more bytes arrive than you might have requested, right? So you want to utilize that bandwidth. All the bytes that travel between the SMs and DRAM, you want to use as many of them as possible because you are paying for them to travel. Another thing to keep in mind is that all the memory access instructions, really just like all the instructions, again, they're executed 32 threads at a time, or one warp at a time. So we really don't look at the address pattern from a single thread. We'll look at addresses from 32 threads and convert those to DRAM requests. And there are things you can do to help the memory system. And this may sound very different from what you've seen on the CPU side, but it really isn't, right? If you look at x86 sockets, to really maximize memory throughput, you need vector memory access instructions, right? Compiler may be generating them for you or may not, but you need SSE or AVX vector memory access instructions. Otherwise, you will not saturate a CPU's memory bandwidth either. And the difference is really that SSE and AVX vectors are per thread, so either compiler has to find those vectors or you have to code vectors explicitly. Whereas on a GPU, we take a group of threads and say, okay, well, this is a vector of threads. It'll give us a vector of addresses, fetch that data. But the underlying concept is the same in both cases. Okay, so as I mentioned, all the data lives in DRAM. Right? In CUDA, there are several memory names, and all of these are sort of logical memory spaces. Right? So we have global memory, we have local memory, textures, constants, and people usually say, well, GPUs have so many memories, it's really complicated. How do I choose which one to use? But the idea behind all of them is really pretty simple. All of the data that's assigned to any of these memories, all of it lives in DRAM, right? So far away from the SMs. So all of it will have to make its way to the SMs. When you access any of that data, it goes through L2. So actually, any access to DRAM, whether it's coming from the SMs, if I can figure this thing out, I can't. Right, so whether SM is accessing DRAM or whether actually the CPU or another GPU is accessing peer's memory, all of those accesses to the DRAM go through L2. So here I showed the path from DRAM to the SM, but if CPU or another GPU were accessing this GPU memory, it still request would have come to L2, and then L2 would have gone to DRAM, and then goes back to L2 and to another destination. So that's something to keep in mind. Okay, now once data gets to the SM, let's say it started in DRAM, went through L2, went to the SM. Now that's where we have these three different caches or buffers. And that's really where texture memory, global memory, constant memory, that's the only place where they make a difference. Because those logical memory spaces go through slightly different paths, but all those paths are on the SM. And really the only question is what kind of bandwidth these buffers or caches have, and how big they are. And which way you're going to go is really purely programmer's choice. So L1 path is the default, whereas read-only path here, or texture cache, or constant memory cache, for those you actually have to do some explicit coding to request that your data travel through those particular paths. And we'll look at how they behave and in which cases you might prefer one over the other. Okay, so L1 path, as I mentioned, is the default one. So all the global memory accesses by default will go through the L1 path. Right? So that's, global memory is anything that you allocated with a CUDA malloc call. It's also any mapped memory on the CPU host. It's also any memory on a peer GPU somewhere else on the PCIe tree. So unless you do anything special, you are going through L1 path. L1 path also caches local memory, but local memory you don't really code to yourself. It's really memory that's used by the compiler, so I'll just sort of skip over that. Now, read-only cache, or also known as texture cache, in order for data to go through that particular path or cache, you either have to have data in texture objects or CUDA arrays, so you have to explicitly put it into the storage format. And with compute capability 3.5 and higher, you can actually add either some intrinsics to force a memory access to go through that path, or do some compiler, function argument qualification. And we'll look at an example of that. So you can force it. And constant path is really the most restrictive of them all. It's very small. It's really intended for things that, values that are accessed by all threads that you run. And we'll see an example of that. Anyway, so access via L1. What's important to realize is that each thread in a warp will be providing an address to the hardware. In addition to the address, a thread will also provide the word size that it's trying to read, right? And the native sizes are, 1 byte, 2 bytes, all the way through 16 bytes, powers of 2. If you are accessing a word of any different size, and we'll go through an example, it's going to get broken down into several assembly instructions to access memory, and those instructions will be of one of these native sizes. Right? So that's something to keep in mind. If you're accessing, let's say, a float3 data structure, as we'll see later on, that's 12 bytes. It doesn't match any of these native sizes. It gets broken down into 4-byte accesses. Okay, so I said all the accesses are per warp, so hardware will get 32 addresses at a time. And then essentially hardware will look at those 32 addresses and convert them into memory transactions to go and get the bytes. It's possible, because of your address pattern, that you'll need multiple memory transactions, right? So if you need n different transactions to go and fetch the required data for all these threads in a warp, you will have n-1 replays of that instruction. Right? And we'll see replays come up over and over again today for memory accesses. And replays are actually pretty expensive. Sort of as a rule of thumb, think of if you have a replay when accessing memory instruction or memory location, whether it's shared or global, replay is probably costing you around 20 clock cycles of latency. That might seem small when I tell you that global memory latency is up to 800 clock cycles. But if you have, let's say, an address pattern that requires 32 different transactions per warp, you have 32 plays of the instruction, multiply that by 20 cycles, you just added about 600 clock cycles of additional latency. So that gets expensive. Okay, so first we'll look at global memory writes, which do kind of go through the L1 path. Writes are really simple. We don't cache writes in L1 at all, or anywhere on the SM. So writes do get cached in L2, nowhere else. And if there's the corresponding line, cache line in the cache, in the L1 cache, a write will invalidate that line and then go straight to L2. Accesses are 32-byte granularity. And if we have sort of a set of 32 addresses, they'll get converted into transactions of these 32 bytes. A transaction can actually be a single, so 1 or 2 or 4 segments, each of which is 32 bytes. And they have to be aligned and so forth. And I have an example so that'll clarify this rule. Another thing to keep in mind is you could have a situation where different threads in a warp write a value to the same address. Right? So what's going to happen is that one of those threads will win, and its value will end up in memory afterwards. Which one will win, we don't define. Right? So obviously it's deterministic because hardware has to be deterministic, but you cannot count on any particular thread to win. So if you need a specific behavior, you'd have to rely on atomics. Anyway, so a few slides that show how 32 addresses will get converted to memory transactions. So here, let's say, is our address space, and let's say we are accessing 4-byte words. So let's say floats or integers. And I've sort of divided them into 32-byte segments. So if we have a warp of threads, and they request a set of 32 addresses, and they just happen to fall into this 128-byte region, and the region is aligned on a cache line boundary, so it's a multiple of 128 to begin with, what's going to happen, we'll have a single memory transaction, which will be 4 segments. And the benefit of having a single memory transaction instead of multiple ones is that you don't have to send the addresses to the memory system several times. So we'll send a single address to the DRAM for this entire region, and then we'll get back 4 different segments. If we have a more scattered pattern, let's say we only have 3 active threads, and those threads request an address from here, an address from here, and a word from here. Well, in this case, we will fetch 3 different segments, and we actually will have 3 different single segment transactions because this transaction cannot really be combined with the other one. They're in different cache lines and so forth. So in this case, we'll have to send 3 different addresses to the DRAM, and then we'll get back 3 segments. Right? So now, and each of these segments is 32 bytes. So if you are only storing 1 float, you actually are sending 32 bytes across the bus, but only 4 bytes are useful. Hardware will add bit masks so that only the required destination bytes are modified. But as far as hardware bus is concerned, it's moving 32 bytes, and you're paying the cost for that. So that's why generally it's nice, it's preferable to keep these coalesced address patterns where you utilize all the bytes that move across the bus. A couple more store patterns. So in this case, we only have 4 threads active, and they request data in these 2 particular sectors. So in this case, you will have a single transaction because, again, hardware can issue a 32-byte transaction, a 64-byte transaction, or a 128-byte transaction. But in order for it to be a transaction, those segments must be together aligned on a transaction size boundary. So here, addresses fall into these 2 segments, so 64-byte region, and that region starts on a 128 address, which is a multiple of 64. If, let's say, I have this address pattern, so I have 2 threads accessing the segment over here, and 2 more threads accessing the segment over here. So as before, I'm requesting 4 different addresses. They fall into 2 different sectors. I really just need this segment and this segment out of DRAM. What the hardware will really do, though, it will fetch all 4 and move them across the bus. So this is essentially going back to the rule on the slide here, that if we have 2 addresses from a warp falling somewhere in the same 128-byte region, but not within a smaller subregion of it, you fetch the entire 128-byte region, right? So here, we have addresses falling within a single 128-byte region between 128 and 256. But then we can actually reduce this region into half, so we'll only grab a half of it. Here, addresses are still falling within the same 128-byte region, But now we can't really cut it in half and just bring half of it, right? That's why we have to, we can't just bring just this portion and service all the requests. Therefore, we bring the entire sort of cache line. So this way you waste more bandwidth. Yes?
Does the hardware change the data from DRAM to L2 and then take the write value from SM to L2 and then move it over there?
Correct. So the question was, is the hardware responsible for moving data to L2 and then into the DRAM? That's correct. So the hardware handles all of that. SM just issues a write operation, and those transactions go out to L2, and then it's up to the memory system to correctly modify all the bytes that need to be modified. Yeah? Okay, so the question was, is this true for all the compute capabilities, and are there any plans to change it? No, so stores have certainly been operating this way for all the compute capabilities, and in a foreseeable future, they'd be the same. As we'll see a little bit later on, reads perform differently from L1's point of view for different compute capabilities, and so I'll mostly focus on the most recent one. Yeah?
So there was a demo yesterday in
Okay.
this context, how does that
Okay, so the question was that there was a demo or a statement that GPU can actually access CPU memory directly without explicit copies. Right. So that works perfectly fine. So let me describe how that would work. So essentially, this goes back to this use case. Right. So what you're describing is that GPU is accessing data that really is in CPU's memory. GPU is perfectly capable of doing that. It will imply a PCIe transaction, but all the transactions from GPU's point of view go through L2 cache. So let's say if a thread running on the SM tries to dereference an address that really is in CPU memory, that request will come to L2, and L2 will send a request out across PCIe bus, grab the bytes, those bytes will come back to L2, and then L2 will serve them back to the thread that requested it.
so then the actual call is still there if
There's not a memcopy call, but memory copy is just a way to generate a number of PCIe transactions. But PCIe bus doesn't really care whether those transactions are coming from a CUDA memcopy call or from some code executing on GPU. Right? But if you want to move data between CPU memory and GPU memory, it has to go through PCIe bus. Yes?
Is there a performance difference between a 1, 2, or 4 segment?
Okay, so the question was, is there a performance difference between 1, 2, or 4 segment transaction? So assuming that you use all the bytes that travel, right? So you have an address pattern that fully uses each of those segments. It's actually preferable to have 4 segment transactions because that reduces the sort of the control information that you have to send to the hardware. So larger transactions are always preferable, assuming you use all the bytes. To roughly quantify the difference, probably somewhere around the 5% range. If you have a completely bandwidth limited code and you give it address patterns that will always be 4 segment transactions or scattered 1 segment transactions, probably somewhere around like 5%, plus minus. Yeah.
All the data paths between the various memories bidirectional simultaneously?
Okay, so the question is, are the data paths between various memories bidirectional? So I guess what you're asking is really, is this connection bidirectional and is this connection bidirectional, right? Okay, so the question, the answer is no. So just like CPU memory buses, these are simplex buses. So they have to switch directions. So if you are doing writes, reads have to wait in the queue, and then you switch the bus direction. And PCIe bus, which we mentioned, that actually is duplex. So it can actually send and receive data at the same time. But traditionally, memory systems, even on CPU sockets, they are single direction buses, and you have to switch the directions. And essentially, when you think about it, that's how really DRAM operates. It can either serve up bytes or you can receive bytes. So it's really coming from that. Okay, so let's get back to reads. Okay, reads. So this is where, so writes are all the same across compute capabilities. Reads are slightly different, but also pretty simple. So there are different compute capabilities, and we are talking about L1 cache. What may not be quite intuitive is that some GPUs don't actually cache in L1. They just use L1 as a sort of staging buffer. So if we look at really old compute capabilities, so compute capability 1.x, whatever x happens to be, those didn't even have a L1 cache, so this doesn't even come up. If we look at compute capability 2.x, so all the 2-point compute capability GPU, so all the Fermis. They actually had L1 caches. That's where they were introduced. And global memory accesses could attempt to hit in the L1 cache. Right? You could disable that functionality, but you could attempt to hit. And current Kepler, so 3.0 and 3.5 capability GPUs, they do have an L1, but it's only used as a staging buffer. Whenever you access memory, Kepler will not attempt to hit your global memory data inside the L1. So L1, as far as caching ability is concerned, is used more for local memory hits and misses, so for compiler's internal use. Other than that, so as I mentioned, there are two instruction types, right? So there are caching reads and there are non-caching reads. And you select them with compiler options. So compiler option, I'm not going to spell it out, but this particular compiler option will give you caching load instructions or read instructions. So if your hardware is capable of hits in the L1 cache, this compilation path will at least attempt to hit an L1. So on access, you go to L1 cache, you try to hit. If you miss, then you go to L2. If you miss an L2, you go to DRAM. And transaction size in these cases is a 128-byte cache line, no longer a 32-byte segment. You always work in terms of 128-byte lines. If you use non-caching loads, you can force those with this particular compiler option. You never attempt to hit an L1. You essentially go directly to L2. If the line was an L1, you invalidate it. And if you miss an L2, you go to DRAM. In these cases, transactions are just like for memory writes. So they're all at 32-byte segment granularity. But you can take 32-byte segments and group them into 1, 2, or 4-segment transactions. And just like for the writes, grouping them into 4-segment transactions is generally better by a little bit. Yeah? Yes, and I have another slide that says it explicitly. For 3.0 and 3.5, CA is kind of ignored as an option. You get the same behavior as CG. Okay, so some address patterns, just some examples, right? So let's say, again, we have a single warp, and it's accessing 4-byte words. And they just happen to be perfectly aligned. The address pattern is aligned on a 128-byte address, and we are requesting words within a 128-byte region. So in this case, if it's a caching load, transaction size is 128 bytes. But we are getting 100% utilization of the memory system because we have 32 threads. Each is requesting 4 bytes. So together they are requesting, in this particular pattern, 128 bytes. And that's exactly how many bytes will move across the bus. So all the bytes that travel are used by the application. Non-caching loads are actually, in this particular pattern, behaving the same way, except now they're issuing a single 4-segment transaction. But you are still using the memory at 100% utilization. Here's a slightly different address pattern. It's just illustrating that threads in a warp don't have to access consecutive locations in sequence. You could have arbitrarily permuted address pattern, but as long as you're utilizing all the bytes within this region, again, you're getting 100% of the bytes that are traveling across the memory bus. Some really old compute capabilities like 1.0, they actually would have tripped on this address pattern and issued multiple transactions. Starting with the 2.0 compute capability, doesn't matter what the address pattern is within a cache line, you just fetch the cache line and then sort it out on the SM side. Same thing with 32-byte segments for non-caching loads. So this is where things get a bit more interesting. So let's say we have threads accessing consecutive locations in memory, but now the address region doesn't fall on a nice multiple of a cache line, right? So we have somewhat offset address pattern. Well, hardware will have to fetch, in this case, 2 cache lines. So we end up doing 2 memory transactions in this case, and each transaction is 128 bytes. So we move a total of 256 bytes across the memory bus, but application is really using only 128 of those. So now we're using the bus at 50% of its efficiency, right? It has to move all those bytes, but we only use half the bytes that got moved. That's where non-caching loads are actually preferable because their access granularity is smaller. Instead of breaking transactions down into 128-byte lines, we break them down into these 32-byte segments. So, and we only fetch the segments that we need in this case. So we are fetching 5 segments. We are bringing 160 bytes over across the bus, whereas we needed 128. So the lowest efficiency we'll get is 80%. In some cases, we'll get 100% if these misaligned addresses sort of shift over and start on a multiple of 96. Then actually we'll no longer need this particular segment. Right? So if you have these sort of not perfectly aligned address patterns and you don't count on cache hits, Non-caching loads are actually preferred. Another address pattern, let's say all the threads in a warp only want one specific word within a cache line. Still, you're going to move the entire cache line, so the warp only needed 4 unique bytes. You moved 128 bytes across the bus, so you're using the bus at about 3% efficiency. Same thing happens with non-caching loads, but instead of moving 128 bytes, you only move the 32 that you need, right? So you waste many fewer bytes from the bus's point of view. Right, so that's why it's important to keep sort of address pattern in mind. Think, how will my addresses, hit the memory system, and how many transactions will I need, and will I use all of the bytes that I bring over? Yeah? Okay, so the question was, if I talk about this address pattern, I'm claiming that I'm saving, bandwidth because I'm only moving these 32 bytes instead of 128. But then can the remaining slots be used by something else? And in fact, they actually can. If you look, you have a lot of SMs, and SMs can actually issue memory requests much faster to the memory bus than the memory bus could consume them, assuming they're all issuing at the peak rate. So if this particular SM says, on this clock tick, give me only this 32-byte transaction, you have another 10, 13 SMs that could be issuing their own memory transactions, and they're all competing for the same bandwidth. And generally, you will run out of bus bandwidth in bytes per second before you run out of request bandwidth. So actually, it does end up being a benefit overall. Yes?
Why are not used not used for global memory?
Okay, so the question is why L1 is not used for accessing global memory. Essentially, the decision was made that, based on codes that we were aware of, we ran them through a bunch of experiments, and we found it's very few of them ever benefited from hits in L1 cache. And generally, we wanted to reserve more of L1 cache for local memory, so register spills for the compiler use. So it was just sort of a call that was made from optimization point of view. There are cases where performance will regress. If in Fermi, for example, your code hit in the L1 cache a lot, now those requests have to go to at least L2 cache, so they're further away. There'll be some codes that will see a slowdown and it'll have to be adjusted. Maybe you have to stage the data through shared memory or go through, let's say, read-only cache or texture cache. But if you look at sort of, the wide application spectrum, overall it was a net benefit to skip the caching. Yeah?
So if you go back to the caching load of
This.
one, so yes, this case. So yes, you're not utilizing all of your data, but what if now things are in cache and the other
Right. Okay, so the question was, in this particular case, this warp doesn't use all the bytes in this transaction, it's wasting some bytes here. But the claim is, okay, what if another warp will need this data and the data resides in cache? Right, so that's where if you hit, you would get a benefit. But in general, I tell people, don't really count on cache hits on GPUs because, if you look at L1 cache on Fermi, it's 48 kilobytes per SM. And you are running hundreds, if not a couple of thousand threads on that SM. So you have a lot of threads competing for this very small cache. So per thread, you have just a handful of bytes of cache. Things usually get evicted, right? Because you have no control of how warps are scheduled. Because each scheduler has its own pool of warps that are waiting, and it's trying to schedule them somewhat fairly. So this particular warp would have brought in these 2 cache lines. But then the question is the other warp going to run in close enough temporal proximity to actually benefit from that? And sometimes it would happen, sometimes it wouldn't. But yeah, potentially it could help there. Actually, I'll get to that in a little bit. Yeah. Actually, I have a section on that too, so let me get to that. Okay, non-caching load. Okay, so this is sort of moving into sort of more pathological address patterns. So we can imagine the worst possible case. Let's say if each thread wants a float, so 4 bytes. The worst possible address case would be I need 32 different transactions. And if I'm using caching loads, for each thread, I would have to fetch its own cache line, right? So not only have to replay the instruction 32 times, so that adds to the latency because, again, each replay costs you about 20 cycles. But each thread needs 4 bytes. That for those 4 bytes of data, I'm moving 128 bytes across the bus. So I'm wasting bandwidth and I'm increasing latency. So that's where non-caching loads, They're still not great, but they're 4 times better, because now for each thread in the worst case, rather than bringing in 128 bytes to satisfy a single word request, I'm bringing in only 32 bytes. And again, so this warp is issuing its request, other SMs will be issuing their own memory request, and it can all happen concurrently. So you'll be wasting less bandwidth with non-caching loads, assuming you don't count on cache hits. Okay, so to summarize sort of, caching versus non-caching loads. There are compute capabilities that can hit an L1 cache. So all the Fermi GPUs, compute capability 2.0, 2.1, 2.3, and so on. In those cases, caching loads are better if you are really counting on hits for performance. In general, I would discourage you from that in the long term as well. Non-caching loads are better if you have scattered access patterns, because in many cases, you'll be wasting less memory bandwidth. Also, whenever a kernel uses a lot of local memory, so if compiler runs out of registers, it has to start backing them into DRAM, which compiler calls local memory. Now, those writes and reads are cached in the L1. So if you want to give compiler more leeway so it can restore registers out of L1 cache rather than going all the way to L2 or DRAM, by using non-caching loads, you do less pollution of L1 for the compiler. And that's kind of in Kepler. It was deemed to be an overall benefit. Okay, so these are compute capabilities 1.x, so some pretty old GPUs, and Kepler 3.0 and 3.5. Whether you request caching or non-caching loads with a compiler doesn't really matter. Hardware will treat them all as non-caching loads and operate at that 32-byte granularity and so on. And as I mentioned earlier, in general, I kind of discourage people from using GPU caches, L1 or L2, in the same way that they would expect to use CPU caches, because size per thread is much, much smaller in GPU. So there are cases where you can benefit from L2 cache hits, and there are cases where you can even benefit from L1 hits on Fermi, but they are pretty few in between. And in many cases, you can actually benefit, instead of L1, by loading data into shared memory. You'll get even better performance and a performance guarantee. L1 sizing, so another quick point. So Fermi and Kepler GPUs, what they really have is 64 kilobytes of SRAM, so static RAM, that is really partitioned between L1 cache and shared memory. So somebody earlier asked about shared memory, and we'll get to it in a little bit. And Fermi GPUs could partition it in 2 ways, so 16 kilobytes of L1, 48 of shared, and the other way around. Kepler SMs add another partitioning, so 32 and 32, so half and half. And you do this with a call of CUDA set, CUDA device set cache config, or CUDA function set cache config. So you really can choose the cache configuration between shared memory and cache, either per kernel, if you really want that kind of fine control, or you can just set it for the entire device for all the functions that you will run on it. And the default partitioning is that you get small 16 kilobyte L1 cache, and you use the remainder of the SRAM, so 48 kilobytes for shared memory. Making this choice, again, so large L1 will traditionally help when you spill a lot of registers, when compiler runs out of registers and generates local memory usage. Large shared memory you would choose whenever your occupancy, or the number of warps or number of thread blocks you can run per multiprocessor is limited by the shared memory amount. Right? If a thread block is using a lot of shared memory and you want to run several of those thread blocks, you probably want to set shared memory to 48 kilobytes. So I think that's all. Okay, so that's all on sort of L1 path. So any more questions about that before we move on to the sort of the texture or read-only path? Okay, so read-only cache. So everything I've described so far was for the L1 path, right? So that was one of those 3 buffers that you can choose within the SM. The other one is read-only cache, and we don't call it texture cache anymore because it's not only used for textures starting with compute capability 3.5. So it is known as texture cache because all the texture accesses do go through the same cache, but you can also have global memory accesses go through this path as well. The restriction is that any kind of accesses through this path have to be read-only. So the compiler, in order to generate these accesses for this path, has to know that if you are reading from that address, that a thread in the same kernel will not also be writing to that address, because this cache is not aware of any writes, so you might be getting stale data. Comparing this path to L1, it has its benefits and it has its some shortcomings compared to L1. So it is generally better than L1 for scattered reads. The reason for that is that it also operates at 32-byte granularity, but it also does caching at 32-byte granularity. Right? If we think about L1, if it is capable of caching, it caches at 128-byte granularity. In this case, you always make requests at 32-byte transactions or segments, but you'll also attempt to cache them and hit them at that same granularity. It also is much better for replays, right? So I mentioned that if you have to have many transactions for a single warp's memory access instruction, L1 path will have to replay that instruction that many times, right? In the worst case, you'll have to play the instruction 32 times, and each time incurs, 20 or slightly higher or slightly more cycles per replay. So the latency really starts adding up. Texture path does not require replays. It handles them much more smoothly. So those are the two benefits. So if you have a really scattered access pattern, texture cache may be preferable, or read-only cache. Now, on the flip side, it does have higher latency than just going through the L1 path. So if you hit an L1 or hit in this read-only cache will take more time to hit. So it does make your memory accesses slightly longer. So you have more latency to hide now. The amount of read-only texture cache, so I think you asked about that earlier. So there is an aggregate of 48 kilobytes per Kepler SM, but it's really 4 different caches. Right? So think of it that Kepler SM, as we saw earlier, has 4 schedulers for instructions. So each of those schedulers gets its own 12 kilobyte cache. And warps that are assigned to a particular scheduler only go to that particular 12 kilobyte cache. And on top of that, caches are not really coherent with each other, even on the same SM, so you could have data replication. If one warp requests a given cache line, another warp running on another scheduler needs the same cache line. Well, that cache line will be in both caches. So that's how this particular cache operates. More on this operation, so it's pretty interesting. So I think this is the first time we describe this operation publicly. So as I mentioned earlier, it always attempts to hit in the read-only cache if you access via this path. Transaction size is always 32-byte queries, as the texture terminology uses. Now, warp addresses. So we still have a single warp, so 32 addresses being provided, but these are converted to transactions slightly different from the L1 path. So L1 path would look at all 32 addresses and try to convert them to the minimal number of transactions. Here, actually, we will look at 4 threads at a time. So we take a warp, which is 32 threads, and we'll look at the first 4 threads. We examine those 4 addresses, convert them to 32-byte transactions. Then we'll look at the next 4 threads, look at their addresses, convert their request into 32-byte transactions, and so on. Right? So if we look at an example, let's say this is for the read-only path. Same access pattern that we saw before, so 32 consecutive locations. But now it's going to get broken down into at least 8 queries, right? Because we'll look at 4 threads, 4 threads, 4 threads, 4 threads until we look at all 32. So the first query are the orange threads, and their addresses fall in this segment, so we request this particular segment from memory. Next, we move on to the next 4 threads, and again, their addresses fall here, so we issue a query to the memory system. So it's pretty straightforward, but slightly different address pattern-wise from what L1 does. So this is a sort of a case that demonstrates that difference. We have the following address pattern. So we have, let's say, these 7 threads requesting the same address, and the 8th thread requests some address over here. So again, in the first query, we'll look at the first 4 threads and request the transaction, the segment that contains the data that they want. Then we move on to the next group of 4 threads, which is these 4 orange guys. Well, in this case, these 3 threads need data from this sector or segment. This one thread needs data from this particular segment. So now we actually will have 2 memory transactions or 2 queries and for this group of 4 threads. However, this particular segment needed by these 3 threads has already been requested by the preceding 4 threads. So we actually will not issue redundant requests to the memory system below, to L2. What's going to happen from the performance counter point of view or even hardware point of view, let's say this was a cache miss and we requested this data from L2. Once we come to the second group of threads, this particular segment, which hasn't been requested yet, again, that's going to be a miss. This guy, since it's already been requested by somebody else, is going to be a hit. Right. So that's where, looking at cache counters, you kind of have to keep in mind that accesses are processed 4 threads at a time. Because if you think, let's say we have a case where all 32 threads need the same exact word. So in this case, we'll have 8 cache queries, because we'll have to look at addresses 4 threads at a time. And what we'll really end up having for a single load instruction, we will have 1 miss, and we'll have 7 hits in the cache. So understanding this operation is important if you are using the profiling tools and you are looking at a read-only or texture cache hit rates, right? Because you might get sort of some non-intuitive results. If you have sort of a single test where you launch a single warp and it issues a single load, you will see 8 cache queries, right? Potentially even more. Yes? Okay, so the question was, the second group of 4 threads here, is it processed for memory transactions only after these guys have completed their request? So the answer is yes, but I'll be a little bit more specific. We don't wait, so the first group of 4 threads, they will issue this request. We don't wait for this request to come back before processing the next 4 threads. So, all these 4 thread groups out of a warp, they get pipelined with each other. They don't wait on the previous one to finish. But as far as conversion of addresses to the memory transactions happens, you do wait. It just sort of happen on every clock tick. So first 4 threads, next 4 threads, next 4 threads, and the next clock tick, and so forth. So therefore, by the time we're doing the second quad or 4 threads, we are aware of what's happened in the previous one or ones if we're further down. And that's how we avoid issuing redundant requests for the same data over and over. Yes? Let me get back to that when I talk about constants. Okay. So accessing global memory versus read-only cache. So we talked how it operates, but now we've got to look at how do you actually write code to go via this path. As I mentioned earlier, the L1 path is the default. If you don't do anything, you are going through the L1 cache or buffer, if you like, on Kepler. To go through the read-only cache path, you have 2 options. You either use the LDG intrinsic, which takes an address and then generates an instruction that will go through the read-only cache, or you convince the compiler that any address that's being read is not going to be written by somebody else in the same kernel. That is a bit hard to convince the compiler of, but I'll talk about that. So if we look at the intrinsic first, that's what the code would look like. Right? So you pass your pointers to the kernel just like you would in any other case. So these are just your regular global memory pointers. And now instead of just simply, let's say, saying input and dereference the IDX element in the array, you get the address of that location and you give the address to the LDG intrinsic function. And now compiler will go and generate, LDG assembly instruction. And that's where, if you're curious whether compiler really did it or not, you can look at the assembly and see, is there an LD instruction which will go through L1, or is there an LDG instruction which will go through the read-only path? If you go the other route, essentially what you try to do is convince the compiler that you'll never have writes to the same location, so the data will not be stale in the cache. Another way to do that is all the pointer arguments to the kernel have to be decorated with a restrict qualifier, because in C standard, it's generally assumed that all the pointer arguments to the function can alias with each other. Right? Also, the data that you want to read with this through this read-only cache path, you also have to specify the const qualifier, because it tells the compiler, I will never write to this address in this particular kernel, right? Because the data is constant there. And restrict really means that no other pointer is alias to this address, so they will not attempt to write there either. So the same kernel, here's what it looks like with the intrinsic, so you have to modify your code inside the function. If you just want to do the decoration of arguments, so in this case, output is the one that we are writing to, and input is where we're trying to read. So both are decorated with restrict qualifiers, and now you're telling the compiler that whatever address I have in input, it will never alias with something that's passed in as output. And I'm also telling the compiler that I will never attempt to write through the pointer passed as input. So now compiler is free to actually generate, in this particular memory access case, LDG instruction. Now, if you call other functions from a kernel or launch other kernels and you pass the same pointers, compiler has to be conservative and will actually revert back to the L1 path, because it may not know what other functions are doing with those pointers or what other kernels that you launch from a thread do. But that's where if you want to double check what the compiler did, you look at a quick dump of the assembly and or you use the profiler. Profile actually has different counters for accesses via L1 path and via the read-only path. Yes?
Can you hook this up by using the reloading hash by stuff that you're going to read multiple times, getting evicted by things that you're reading in the world?
Okay, so very good question. So the question was, let's say you have a situation where some of the data is being reused, so it gets accessed multiple times. Some other data gets sort of just streamed, right? So does the pollution hurt? And like with any other hardware-managed cache, yes, pollution can hurt, and many times it will. Right? So if you have data that's reused frequently, you're kind of hoping that it gets accessed and its flag gets reset for the least recently used, maintenance hardware on the chip. But all the other data that just sort of streams through the cache once, somebody requests it and nobody else ever needs it again. They all compete for the same cache line space. And if you start running out of cache lines, you'll start evicting others, right? And you may be evicting things that you want to hit again. So that's where hardware does have the least recently used mechanisms and so forth, but that can only do so much when the cache is small. And that's sort of another case, sort of like a ninja programming technique. Some people know, let's say on Kepler, they have some data that they count on hitting by multiple threads or several times. Other data they just stream. Right? So this, for example, happens in sparse matrix vector multiply, highly tuned kernels, where the matrix really just gets streamed for the multiply, and the vector based on the matrix structure could be getting reused in various output elements. So they read the vector via the texture path. The matrix is read via L1 path. And by reading them through these different paths, you actually guarantee that things that are only being streamed, that they never have any kind of hope of being hit in the cache, they go through some other path that doesn't pollute the cache where you are hoping for hits. And again, so this is sort of, as I mentioned, sort of a ninja technique. It might get you another 10% on that order of performance, but that's something to try if you're really trying to squeeze all the performance out of the GPU. And having these different code paths, or memory access paths helps in this case because you do get a choice if you want it. Okay, so I'll just very briefly state additional texture functionality. So everything I talked about is global memory. However, if you choose to put your data into CUDA arrays or CUDA texture objects, you do get additional functionality in addition to sort of caching and memory transactions and so forth. And all of these are free. They basically come from the graphics world. Right? So things you get are out-of-bounds index handling, and I have a slide illustrating that. So if you have out-of-bounds accesses for global memory and GPU, it's the same problem as on CPU. If you access some invalid data, on CPU you'll have a segmentation fault. We'll have the same thing on GPU, except we call it unspecified launch failure. Right? It's as informative as an error message as is segmentation fault. But we do have CUDA memcheck, which you can run through it and it'll at least tell you to point, okay, well, it was this access that was out of bounds, and you can track it down. It's kind of like Valgrind for GPU. You do get optional interpolation. If you have 1D, 2D, 3D texture object or CUDA array, think of it as you have an array of data, but you are using floating point indices into this array, which at that point triggers interpolation between the closest elements. And lastly, you do get optional format conversion. So the data that you store in a texture object can be characters, it can be short ints, single precision, 16-bit floating point representation. And as part of the data fetch, actually, so the data is stored in this format in the DRAM and in the cache lines. But when a thread is actually getting the data, it can get converted to a single precision float. And again, there's dedicated hardware for that, so there are no additional operations that you incur. So this just sort of illustrates two things. So here I illustrate the indexing, because for texture objects, and this is no longer like sort of regular memory, you have to allocate special objects and pass them to your kernel. You have, in this case, let's say two-dimensional data. So that's, let's say, 4 columns, 3 rows. But now the thing to keep in mind, you are providing floating point indices into this array. So the integer values, like 0, 1, 2, and so forth, those don't fall in the center of a data cell. They fall on the edges between the cells. So if we look at the two addresses here, so for the blue dot, which falls dead center in a particular cell, you really have specified address that's 2.5 in the x dimension and half in the y dimension. Right? So that's how you go dead in the center. If you give it integer coordinates like 1, 1, you are looking at basically division between 0th and first column and 0th and first row. So you're requesting something that's really right at the intersection of 4 texels. And if you have interpolation enabled, essentially you'd get a linear or bilinear interpolation of those values provided back to you. This just illustrates the address or out-of-bounds clamping or processing. So here you have a data array, but if you specify coordinates that are 5.5, 1.5, really you specify an index that's falling outside your data. But texture hardware is aware of the dimensions of the array, and the index wrap mode will essentially just wrap around and request some valid data element from the array. Some applications benefit from that. Clamp is probably more intuitive. If you specify something that's out of bounds, it gives you the closest value that's still valid within the data range. And again, this happens automatically. You don't have to put if statements in your code. Texture objects and hardware have that functionality built in. Constant cache. So I think you asked about it earlier. So this is the third and last path to access DRAM data. It's also the most restrictive one. So if we look at its performance, first of all, the data that can be accessed via this path is limited to 64 kilobytes on the GPU total. That's it. Right. So that's why it's called constant cache, because it's really used for a small set of constants that are uniformly used by all threads. And it has to be pretty small because that's all you have to work with chip-wide. In order to use it, all you have to do is to have a globally scoped array declaration, and you proceed it with a constant qualifier. And then all those requests to that array will be going through the constant cache path. Constant cache actually has pretty low throughput. It has 4 bytes per clock tick per SM. Right? So this is why address pattern is very important for the constant cache, because if you have 32 threads requesting 32 different addresses from the constant cache, you'll have 32 replays of that instruction, because we can only service 4 bytes at a time. So really, if you are considering constant cache, you have to know that all 32 threads in a warp, and preferably thread block, will need the same exact element with a particular instruction. Then actually it's beneficial. And the reason you might want to do it, use it, so sort of following up on your question earlier, if you have some small set of data, let's say 64 kilobytes or smaller, that all the threads will be reusing frequently, so let's say like finite difference stencil coefficients or things like that. And you want to put them through some path that other memory accesses don't pollute, this is a way to do it, right? Because now these go through their own dedicated constant cache, everything else goes through read-only path or L1 path, and they will never pollute this cache. So that's where you get this behavior. And typically, where I've seen the use of for these is, for any kind of discrete, finite difference schemes, you put the finite difference coefficients in this memory, and they live there. Yes? Okay, so the question was, if you look at a warp, we can service 4 bytes per clock tick per SM. So how many different addresses can you have per warp before constant cache is no longer practical? I don't have that number off the top of my head, but it really would depend on the code, right? Because essentially, if you need several different words per warp, you'll have to replay that instruction, and again, you're incurring that 20 clock cycle latency for the replay. So it really increases the latency for you to get the data back. So if some instruction is using a constant value, now that instruction will just have a much higher latency. And now if you have plenty of other warps that can do something else in between, it doesn't really affect you, but if latency is a problem, you'll start seeing performance drop. So it's hard to answer it, but generally, the way I do it, unless all the threads in a warp will request the same value, I just don't do the constant path. But I really haven't investigated it. Okay, I guess the code sample of what it looks like. So here you have, at global scope, you just have some array, let's say coefficients. All you do is just add the constant qualifier to it. Then somewhere in the CPU code, you have to load up the data to that array. So you have something like CUDA memcopy to symbol. You give the, the symbol name of that array, and then, pointer to memory where you want to copy data from CPU to GPU, how many bytes, and so forth, the traditional thing. And somewhere inside your GPU kernel, you use that array just like you would use any other memory dereferencing. Right? It's the only thing that you do. You have to qualify at global scope and then load the data into that array, compile it, and it automatically converts it. There's nothing special you have to do inside the kernel afterwards. Okay, address patterns. So I'll just mention these. Obviously, we're already way out of time. But if you look at previous year's GTC slides, which you can find by following this, sort of the offset address pattern, which we looked at, large strides, contiguous regions per thread, irregular scattered addresses, they will all be moving more bytes across the bus than the application requests. And there are actually ways you can diagnose that you have one of these cases in your code by looking at the profiler signals. And there are various things you can do by padding your data, converting the data storage format, and so forth. So I actually walked through all of these in last year's slides, and there are use cases with examples. So I encourage you to look at those because we don't have time. I'll just look at a single case today, right? So let's say what we have, we are accessing a 12-byte structure per thread. So something like, position structure, which has 3 floats in it. So that's a 12-byte structure. We don't have 12-byte native access word. And let's say, some access like this in the code. So what's going to happen is compiler will take this assignment where we load from global memory a structure of 12 bytes. It's going to break it down into 3 different loads over here, and each load will be 4 bytes. We can't really group it into 64-bit and 32-bit loads because we will not get alignment. So what's going to happen is something like this. First load instruction will load this data for the first thread, this data for the second thread, and so forth. And all the spaces in white are not really used in this case. But we are fetching this 32-byte segment and this 32-byte segment and so on. Then we go to the second instruction. It's requesting the second element now for each thread. And we are refetching the same transaction. Let's see if we're not using the caching loads. And the third instruction will bring in the remaining bytes. And effectively what we've done, we have requested these memory segments 3 times redundantly, right? So how to go about it? And you'll actually see performance drop because of this. We waste quite a bit of bandwidth because we move 3 times as many bytes as we need to. So potential solutions are, change the data layout. You could try going through the cached path, which is, read-only cache, or you could try stage them through shared memory, right? And here's sort of the performance or speed-ups for them. So the kernel that did nothing but read memory. So the original format, let's say that's performance, unit 1. If we went through the read-only path, which does some caching on the SM, we get 1.4x speedup. If we go through shared memory staging, we get 1.4x speedup again. But really converting your data storage to structure of arrays as opposed to array structures gives the best speedup at 1.5. And for writes, we have slightly more performance. And the speedups, the reason they're not 3x, because we were getting hits in the L2 cache. And L2 cache has roughly twice as much bandwidth as DRAM. So we generated 3 times as much traffic, but all the sort of redundant traffic hit in L2, which had twice as much bandwidth. So that sort of explains the 1.5 number that we see. OK, so this was just the address pattern. So let me touch on latency hiding really quickly, and then we'll decide what to do next. So to keep the memory bus busy, we have to issue enough memory requests. And to really know how many bytes you have to have in flight at any given point, you take essentially the latency for memory access, and you multiply it with bandwidth. And this will tell you the total number of bytes that have to be traveling on a bus at any given point in order for you to hit that theoretical bandwidth or close to it. So to give some more intuition into this multiplication of bandwidth and latency, let's consider the escalator example, right? So let's say we have an escalator, and what you have is, one person fits on each step, and a step arrives every 2 seconds. So from this, we can get our bandwidth, right? From the arrival point of view, we get 1 person arriving every 2 seconds. So if we say that 1 second is our time unit, we get half a person per second. That's our bandwidth for this escalator. The escalator is also 20 steps tall, and a given step, so we have 20 steps that we have to travel through, and then we move a step every 2 seconds. So the latency from the moment we get on the escalator till we arrive at the top is 2 seconds per step. We have 20 steps to traverse, so latency is 40 seconds. So you can sort of view this as our memory bus. Latency is 40 seconds. Bandwidth is half a person, half a transaction per second. So if all we do is put a person on an escalator and wait for that person to arrive at a destination, then we put the next person on and that person travels through, we actually are spending 40 seconds waiting for 1 person to arrive at the destination. So the bandwidth that we really achieve is 0.025 persons per second, which is, 20 times smaller than the bandwidth that we have, half a person per second. And the reason we're not getting the full bandwidth out of this escalator is because we're not keeping it busy, right? So the way to keep it busy is to make sure that, as the person arrives, in the next tick of time, which in this case is 2 seconds, the next person arrives and so forth. So we have, persons on every single step. So we're loading up this escalator or the memory system. So what you really have to do, we know that the latency for arrival is 40 seconds. And out of those 40 seconds, every 2 seconds, we can put another person on the escalator to travel up. And that's what you want to do. So for every time unit or every clock tick, you want to put a memory request on the bus. And to get the total number of bytes that are on the bus, or total number of people on the escalator, you multiply the bandwidth, because you can put bandwidth number of persons on the escalator in every time unit. And you multiply with the latency, because once you put something on the escalator, that person will need latency seconds to arrive. So that's sort of the intuition there. If we convert it to GPUs again, so here we'll actually look at the lines in flight per SM. So again, a line is 128 bytes. And what I have on the y-axis is really just a percentage of the theoretical memory bandwidth that the GPU has. On the x-axis in this experiment, I varied how many lines were traveling on the memory bus from this SM at any given point. Right? So I hacked up the code to force the numbers to be low. So we see if all we have is 16 cache lines traveling on the bus at any given point, we only achieve about 20% of our theoretical bandwidth of the GPU. So we do need to add more and more concurrent memory accesses in flight to saturate the memory bus. And somewhere around like 100 accesses, 100 cache lines in flight, we start saturating the achievable memory bandwidth. So as I mentioned, so Kepler GPUs need about 100 lines in flight, where a line is 128 bytes. If you want to reword it in terms of 32-byte segments, because some memory paths access memory in 32-byte segments. So you need about 400 32-byte segments in flight per SM to saturate the memory bus. So that's quite a bit of memory accesses you have to have concurrently. The way increased memory accesses is sort of, you can look at your occupancy, run more threads concurrently, and each thread issues its own memory accesses, or you give more memory accesses per thread. Right? So for example, if a thread is producing a single output point, if you change your code to process 2 output points per thread, now it really has sort of 2 independent code paths within a thread, so they can interleave them, and you just double your memory accesses per thread. Your register use will go up, but as long as your occupancy doesn't drop in half and memory accesses go up by a factor of 2, it's a net improvement. So here's another sort of quick case study to give you some more intuition in the performance benefits that could happen. So this is VTI RTM kernel, which is 3D finite difference. It doesn't matter what it does. But in this particular case, our resource consumption by the code, so registers, shared memory, allowed us to run at most 42 warps per SM concurrently. Now, the code initially chose 32 by 16 thread configuration per thread block. So a warp is 32 threads, so we were running a total of 16 warps per thread block. Since we only assign warps to an SM in discrete thread block sizes, we could at most run 32 thread blocks 32 warps at the same time. Right? We didn't have enough resources to go to 48. And we also identified that insufficient concurrent accesses were the problem, because the code should be memory limited from early analysis on Profiler. Access pattern was perfect. We were using all the bytes, but we were only achieving 37% of theoretical memory bandwidth. So what we did is change the thread block dimensions to 32 by 8. So now each thread block is 8 warps, and now we can squeeze more of them in, right? Because each thread block is 8 warps. We can actually run 5 thread blocks concurrently, which gives us 40 concurrent warps per SM, as opposed to 32 before. So we increase number of warps by 25%, which automatically increased the number of memory accesses by 25%, because each warp has its own accesses. And the overall speedup was 1.28x, so about the same amount percentage-wise, right? And the code change was really simple. We had to change one value in the thread block sizes. And that's where Profiler kind of helps. You can look at occupancy and so forth. All right, so the takeaways for memory, 2 things to keep in mind. Strive to have access patterns that utilize all the bytes, or as many bytes as possible, that travel across the bus. And then the second portion is make sure you give enough memory accesses to the memory system to keep it fully occupied to get the full bandwidth. So unfortunately, we're right at 11 o'clock. So I don't care. I can keep going because there's lunch and I have nothing else to do. What we have left is, let's see what slide that is. Yeah, we have a few more slides. So I can talk about shared memory and then talk a little bit about parallelism. So I don't know what the general feeling in the audience is. Okay, so I'll keep going. And hopefully all of that can be recorded. Okay, so shared memory. So shared memory, so we saw this diagram earlier. We saw that an SM has, sort of these 4 caches of buffers, but the last one was always masked out. So this is shared memory inside the SM. And we talked already that 64 kilobytes of SRAM is split between shared memory and cache. Now, shared memory, you probably have seen in the CUDA basic slides, is sort of user-managed cache or scratchpad memory, so you actually have to write the data and read it from there explicitly yourself. But the benefit is that hardware will not evict anything out of there for you. Right? Any kind of hardware-managed cache will potentially evict data before you use it fully. Shared memory gives you the guarantee that whatever we put there is there until you yourself evict it. It has 20 to 30 times lower latency than accessing DRAM. Also has about an order of magnitude more bandwidth than DRAM. I think, yes? Comparing shared memory to level 2 cache, latency-wise, it's about 5 times lower, so 10 to 15 times lower latency. If I think about DRAM and L2, L2 has roughly half the latency of DRAM and roughly twice the bandwidth of DRAM. So then we can sort of, you take these values and divide it by 2, and you get the relationship of shared memory to L2 cache. Also, it's accessed differently, so it's much more flexible than sort of, cache line or segment accesses to memory, and we'll look at those. Accesses to shared memory operate exactly in the same way as anything else. You have 32 threads, they generate 32 addresses, and those get converted to actual accesses to the hardware. So now what happens with the reads? With the reads, we'll actually go to shared memory banks, which will fetch the requested words and route them to the destination threads. So shared memory actually is fully capable of multicast. You could have several threads accessing the same location, and the data will just get broadcast to those threads in a warp. Bank conflicts, which we'll describe in a moment, will cause replays, and those are getting expensive because they add to latency, about 20 cycles every replay. Writes, again, same thing, same idea. You take the 32 addresses, convert them to actual hardware accesses, and if there are no bank conflicts, you don't need replays. And if you have several threads writing to the same location, just like in the global memory case, one of them will win. Which one wins, we don't specify, so don't count on any specific thread to win if you care about which one wins. Okay, so shared memory banking, that's really how hardware is organized. So there are 32 banks on Kepler, and each bank is 8 bytes wide. And I have some pictures to illustrate that next. Throughput is, in every single clock tick per SM, each bank can serve up 8 bytes. So 32 banks times 8 bytes, that's 256 bytes per clock per SM. So if you look in aggregate per GPU, like K20X, that's 2.6 terabytes per second. Right? Now, it's not contiguous memory, it's spread across different SMs, and each thread gets its own, but that's the total bandwidth that you have. But that sort of gives you the picture of how much faster it is than accessing something that's in DRAM. So if you have a lot of reuse, and you can put the data that's reused into shared memory, all the subsequent accesses will be going at really high bandwidth. It has 2 modes in Kepler. There are sort of 4-byte access mode and 8-byte access mode. 8-byte access mode is really easy to describe, so we'll do that next. 4-byte access mode is really there for backwards compatibility with Fermi. Fermi had 4-byte banks, so they were half as big, half the bandwidth. But if your code was doing some padding to avoid bank conflicts on Fermi, if you switch to 8-byte banks, you might get some additional conflicts on Kepler. So for backward compatibility to really give you the same exact functionality as Fermi, by default, we always run in 4-byte mode, and you can enable 8-byte mode if you want some extra performance. And you select it with CUDA's device set shared memory config function. Okay, so operation of banks. So this slide, I guess, is sort of nitpicky if you want the very specifics. So I'll just sort of talk more intuitively. If you look at, so let's say we have some array that we will put in shared memory. Right? And let's say 4-byte words. So these are really the byte addresses, so 0, 4, 8, and so forth. And in red, I'll just have the indices into my data. So 0 is the first 4-byte word, 2 is the third, and so on. And below here, I really have shared memory hardware. So this is what your program sees as an array. This is what hardware views. So hardware has 32 banks, and each bank is 8 bytes wide. And in 8-byte mode, we have to understand how the sort of array indices or words are really stored into different banks. And it's done in a really simple way. You take the first 8 bytes of your data structure, and it goes into the first bank. You take the next 8 bytes, they go into the second bank, and so forth. And then you wrap around, right? So we store 64 words, which is a total of 256 bytes. And then we start again at bank 0 and repeat this again and again and again. So you can sort of view that banks are, you have these sort of columns of 8 bytes wide and so forth. If we look at, so I'll skip to this slide really quickly. Same exact array, but now we are in 4-byte mode. So this one you really don't have to understand unless you're really trying to get some weird access patterns. What hardware does to guarantee Fermi behavior is going to do now an act that successive 4-byte words go to successive banks. If we look here, successive 8-byte words went to successive banks, right? These 8 bytes go to the first bank, these 8 bytes go to the second bank, and so on. In 4-byte mode, you want the same behavior, but at 4-byte granularity, because that's what Fermi did. So here, if we look at first 4 bytes, so index 0 goes into the first bank. The next 4 bytes, or index 1, goes also into the next bank. So what we really do, we take successive 4-byte words and assign them to different banks, sort of in round-robin order. Once we get to 64 or to 32, we wrap around and fill out the remainder of that bank. So we get to word 31, and word 32 actually goes back and fills out the half of the bank that we didn't use before. So it sort of gives you this interleaved pattern. And if you want to know exactly how hardware does it, so you can take sort of the memory address in bits, and the lowest order bits just identify bytes within a 4-byte word. These guys identify the bank, and then so on. But so if you want, this is the specifics for you to look at. So that's how shared memory operates. The reason banks are important is, I mentioned earlier, you can have bank conflicts. Right? And a bank conflict occurs when 2 or more threads in a warp are requesting different words from the same bank, which will cause replays. So it's actually easier to show in pictures. So let's say, again, we have our warp, and it produces 32 addresses. And it just so happens in this case that every request goes to a different bank, so we have no bank conflicts. We'll get the maximum bandwidth out of the memory system. Here's another pattern. Accesses actually are not sequential, but as long as all the warp address or thread addresses fall somewhere else in a different bank, no bank conflicts. Here's a case actually where we have 2 different threads accessing data in the same bank. But there is still no bank conflict because earlier I mentioned we have broadcast and multicast capability. So here, really what happens, a bank can serve up 8 bytes out of it. So what here, we have 8 bytes from this bank, and the bank will provide this data to the SM, and then the SM will broadcast the respective bytes out of that 8-byte word to the threads that request it. Same thing happens here. These 2 threads happen to need the same word. The bank hardware will really return all of these 8 bytes, and then circuitry will route those, the requested bytes to the specific threads. Here, actually, we get into situations where we do have bank conflicts because we have 2 threads accessing different 8-byte regions in this particular bank, right? So hardware will first serve up these 8 bytes, give the data back to this thread. Next, actually, it has to access a different location within the bank and return this data to the thread. So we'll say we have a 2-way bank conflict in this case, and an instruction will have to get played twice. So first we service this thread and the remaining threads, and in the next replay we service the threads that haven't been serviced yet. And each replay is causing you about 20, on the order of 20 clock cycles of latency. Right? So in the worst case, if you have 32 replays, if let's say all 32 threads are accessing data within the same bank but different words, you'll have to replay the instruction 32 times. And at this point, latency-wise, it's very close to what DRAM has, right? So you kind of want to avoid high bank conflicts. So here's an example of a three-way bank conflict, right? We really need 3 different words out of a bank. Therefore, we'll have to play the instruction 3 times. So quick study of performance impact. So matrix transpose code, which I think you've seen to death by now in various CUDA basic talks. The idea is that we read a tile from global memory to shared memory, and then we transpose it in shared memory and write it back to global memory in a transposed fashion. So you are staging data through shared memory to ensure memory coalescing, to ensure optimal memory access patterns. So let's say initial or simple implementation, what it does, you have a single warp that will read a row of values from global memory and write that row into shared memory, right? So you, from global memory to shared memory, and in order to do the transpose after the sync, what you will have, you have a warp that will read a column of data from shared memory and write it to a row in global memory. So that's, you write a row, you read a column, you just accomplished the transpose. It's this column access that will cause bank conflicts, right? So if we sort of look at it pictorially, so this is our array. That's, let's say, 32 by 32 doubles, so 8-byte words in Kepler. What I have in colors are IDs for different banks. So data that goes into bank 0 is sort of highlighted in green. bank 1 is orange, or whatever that color is, and so on. And warps I have at the top. So warps are indicated with numbers, and I guess banks are indicated with color. So if a warp is reading a column out of the shared memory array, what's going to happen? So the first warp, so 0th warp, first thread reads this data element, second thread reads this data element, and so forth. We need all of these guys, but they're all coming from the same bank because we just have sort of this perfect match. We have 32 banks, we have 32 columns in our data, and everybody's accessing the same data in a single column. So we'll have to replay the instruction 32 times. And Profile is actually very good about pointing this out. So the solution in this case is simply take your data set and pad it by adding an additional row. You don't really have to do anything else. You keep the same indexing. It's just whenever you declare a shared memory array, you add a column of padding, and this will have the following effect. So the access pattern now, array is 32 columns by 32 rows instead of 32 as before. The warp still accesses the data in the same column, but by adding this one additional element here, we have permuted the bank order. So the very first element in the array goes to bank 0. Also, the 33rd one maps back to bank 0. But if we look at it now, all the threads in the same warp in a column will be accessing different banks. Therefore, we have 0 bank conflicts, and we get the maximum performance out of shared memory. Performance-wise, so we kind of talked through this. Performance-wise, the speedup was about 2x. The reason it's not 32 is because what we're doing global memory read, which is expensive, shared memory write, shared memory read, global memory write. So we have 2 global memory accesses, so 2 DRAM accesses, which are very expensive, and in between we had shared memory accesses. But by this speedup being 2x, this is showing that when we had 32-way shared memory bank conflicts, they were as expensive as accessing global memory, right? Because by optimizing away the bank conflicts, we reduced the time in half, right? So that's the impact. So takeaways or summary for shared memory is that it has very high bandwidth, much lower latency than DRAM, and really the only thing to look out for is these bank conflicts. And again, I refer you to the profiling tools. They will point out memory bank conflicts. And bank conflicts are really a concern if they are really high way. If you have, let's say, 2-way or 3-way bank conflicts, most likely that's no big deal. If you have 32-way bank conflicts, you should probably fix them. And the good news is that these high, large-way bank conflicts are very rare. And when they happen, they are very, very easy to fix. Usually it's just the padding of your array fixes the problem. So it's just something to be aware of. Okay, so let me do a couple more slides and we'll really finish. So I'll skip a bunch of those. And actually, pretty much all of these slides you can find in last year's presentation. So if you want the pleasure of listening to me talk through them, you have that online. Okay, so in general, we sort of talked about how memory system works, how SMs work for execution, and we sort of talked about latency hiding, but not putting it all together. So we've seen that within the SM, you need a lot of parallelism to really saturate its pipelines because of instruction latency. If we look at only single precision math, let's say on Kepler SM, you need about 1,700 independent instructions spread across all kinds of all different threads to really saturate the SM. For bandwidth, we saw that we need about 100 independent cache lines in flight per SM. So there's quite a bit of parallelism that you need for both saturating math pipelines or saturating the memory system. And as we saw, what ultimately hardware needs for arithmetic pipelines, it needs enough parallelism, whether it's coming from ILP or different warps, to hide the latency of other arithmetic operations. For memory system, in addition to address patterns, you need enough accesses in flight to saturate the memory bus. And there are 2 ways to do it. You can either have more independent thread per thread or a warp, or you run more independent threads or warps at the same time. To the hardware, it's really the same thing. So that's where the concept of occupancy comes in. So occupancy, there are several definitions. So you can either look at occupancy as a percentage of, if you run X warps, what's the theoretically largest number of warps on this SM, and occupancy is just a percentage of the theoretical maximum. I kind of prefer to talk about occupancy as the number of warps that are running concurrently, rather than a percentage. And occupancy is determined by several factors, right? And to really get all the details, again, I refer you back to the CUDA programming guide and occupancy calculator. They'll expose all the details to you. But the main things are the resources. Each thread consumes some number of registers as determined by a code, right? And there are so many registers in NSM. If we look at Kepler-SEM, there are 64K 32-bit registers, and they have to get partitioned across the threads that run at the same time. Shared memory is another resource. That's allocated per thread block, but you have up to 48 kilobytes of shared memory, and it's going to get partitioned among the thread blocks that run at the same time on the SM. And finally, there are limits to how many warps you can run per SM, how many thread blocks. So if we look, we can run up to 2048 concurrent threads, or 64 warps at the same time per SM. And I think Jim earlier asked about the number of concurrent thread blocks. On Kepler, that's 16. Right? So this is one of those cases, if your thread blocks are really small, you'll run only 16 of them at most. Okay, so occupancy and performance. So many people at first, when they start programming for GPUs, they go, I need to achieve 100% occupancy or run all 64 possible warps per SM. And that's really not the main requirement. You often will get away with many fewer warps than 64 per SM and get very nice performance, because ultimately you don't just want to occupy all the warp slots, you just want to have enough warps to hide various latencies. So, and that will depend on the code. The more independent work you have per thread, per warp, the fewer warps you need, and vice versa. As a rule of thumb, memory-bound or memory-limited codes need more warps to keep the memory saturated. So that's why I usually say on Kepler-SM, strive to have at least 32 warps. That's a good starting point. For memory-bound codes, you may end up wanting more, unless you have a lot of independent accesses per thread. But that's, again, you start with something, and you look at the profiling tools and go from there. So for occupancy, as we saw on the one example where we resized the thread blocks, and all of a sudden we ran more thread blocks. So we can look at that sort of visually. We need to expose enough parallelism, so we've seen that a bunch of times. When sizing your thread blocks, there are two things to keep in mind. Your thread blocks can be too small, because you only run 16 thread blocks per SM at most. So if they really are tiny, that limits the number of warps you run. They can also be too big, because you have this quantization effect. So that's actually easier to show visually than to talk about. So this is the case where your thread blocks might be too small. So let's say in the blue sort of line here, I'm showing the number of warps for which we have resources on the SM. So as far as the SM is concerned, it has enough registers, enough warp slots, enough shared memory to run this many warps. But we are launching very, very small thread blocks. Let's say single warp thread blocks, only 32 threads per thread block. Well, now we are limited by the number of thread blocks that are allowed per SM, which is 16. So we really are only running this many warps, whereas we could run more. So by simply sort of rearranging your threads into bigger thread blocks, now we have much bigger thread blocks, we run 4 of them, and now we fully utilize all the resources that were available. Right? So your thread blocks could be too small. The opposite is also possible. You could have too many threads per thread block, as was in that VTI RTM kernel that we initially looked at. So we have enough resources for this many warps, but our thread blocks are pretty big. So we have enough resources to run 2 of them. We don't have enough resources to run 3, but we still have resources left over with just 2. So by making the thread blocks a bit smaller, we can run 5 of them, and now we fully utilize the resources. And if each warp has its own memory accesses, now we issue more memory accesses to the system. So that's exactly the case study we looked at earlier. We could have run 42 warps by the hardware requirements, but thread block sizes were 16 warps each, so we could only run 2 of them, a total of 32 warps. We cut down the thread block size to 8 warps, and now we can run 5 of them, get up to 40 warps. So we still have some resources available, 2 warps worth, but I stopped optimizing at that point. So actually, let me skip through the remaining slides. So I talk about waves and tails. So the idea is, maybe I'll just touch on it briefly. Whenever you launch thread blocks, they sort of get executed in these waves. So these are all the thread blocks that can run at the same time on the entire chip. And then at the very end, you may have only 1 thread block remaining to run. So we call that a tail, because now it doesn't fully occupy the GPU. Right. If the GPU can tolerate 4 or run 4 thread blocks concurrently, but you launch 5, there'll be a point in time where only 1 of them is running. So this one guy is underutilizing the GPU by itself. So again, if you make thread blocks smaller, the total amount of work is the same, but now you break it into finer pieces, and the tail is still there, but now it occupies a larger percentage. Same thing with the number of waves and so forth. So the takeaways are really for thread block size choices here. It may sound like it's kind of a weird thing. You could have thread blocks are too small, thread blocks are too big. But in practice, it's really pretty simple. Generally, what I tell people, start with whatever makes sense for your application. And if you can, start with, let's say, somewhere between 128 and 256 threads per thread block. And that's a pretty good starting point. It's not too big, not too small. And you may want to adjust it for your application, either for optimization or make code more intuitive if it just breaks down to your application better. Generally, I'd say either allocate thread blocks that are multiple of warp size, 32 threads. It's also not critical, but just keep in mind, as we saw at the very beginning, however many threads you request per thread block, you are going to get a multiple of 32. So if you have a choice to actually use all 32, or all multiples of 32, then might as well do it. So, don't allocate a thread block that let's say is 257 threads, right? Because the last warp only uses one thread out of 32, if you can help it. Grid size, so the number of thread blocks in general, I sort of suggest to people that ideally a kernel launch would have 1,000 or more thread blocks in it, if that's feasible in your code, essentially to deal with these kind of effects, to sort of minimize the percentage of time spent in the tail. Right? If the amount of work is the same here and here, but thread blocks are larger here time-wise, well, tail is a larger percentage of time than in a smaller thread block case, so you run at slightly higher utilization. But again, if you cannot launch 1,000 thread blocks or more for a given function call, you may still occupy the GPU if by launching additional kernels to run at the same time and so forth. So concurrent kernels, CDP are supposed to help in these cases. So this is the end. So we've sort of walked through how GPU performs, but sort of backwards, right? Because as I mentioned earlier, the most important thing is give GPU enough work, expose enough parallelism. Once you do that, then you worry about memory access patterns. And then once memory is sorted out, or if you're instruction limited, then you care about warp divergence and code paths within a warp. And as always, nowadays, just use the profiling tools because they're available in Windows and Linux. We have command line tools. We have tools integrated into Eclipse and Visual Studio.